Welcome to Math Primer for General Physics. This is a review of basic mathematical skills that you will need in order to succeed in General Physics 1 as well as General Physics 2. If you look at the description below, you can see that I have separated all these different sections along with their timestamps. So if you already know one section and if you want to jump into a different section, please use the timestamps to go back and forth within the video. So I'll start by talking about exponential rules and do two examples on applications of these rules. So if you see a number like this, let's say 10 raised to the power 5, this 5 is what we call the exponent. And then this 10 is usually called the base. Now, there are several rules that you need to know, especially when it comes to simplifying these numbers with exponents. For example, you can see over here, when these numbers, they have the same base, and when you have a product of those numbers with the exponents simply add up. So as an example, we can talk about a number like this. So base 10, 10 to the power 5 multiplied by 10 to the power 3. You can see it's 10 to the power 5 plus 3, or we can write 10 to the power 8. The second one is where you have the same base numbers, but now it's a division. So then the exponents basically subtract from one another. Something like this, 10 to the power 6 divided by 10 to the power 2. So that means you can write this as 10 to the power 6 over 10 to the power 2, and the exponents subtract from one another. So you get 10 to the power 4. And this one is the product of the exponents. So let's say 10 to the power 2 times raised to the power 3. So you can write this as 10 to the power 6. Then this one, here you can see it's a fraction raised to some power. And let's say that the fraction includes numbers that are like, 5 and 7. So 5 over 7, and it's raised to the power 2. So then we can distribute this exponent among the numerator and the denominator. So you have 5 raised to the power 2 and 7 raised to the power 2. The other one is the negative exponent. So if you have a number with a negative exponent like this, you can write the reciprocal of that, 1 over number, and then what happens to the exponent, its sign changes. So if it's a negative exponent, when you take the reciprocal, the exponent becomes positive and vice versa. And then this one, that's the fractional exponent. So let's say that you have square root 10 to the power 4. So then we can simplify this as 10 raised to the power 4 multiplied by 1/2, because square root means like 1/2 power to the 1/2. So then you get 10 raised to the power 2, or 100. Another one, let's think about like a cubic root. So that is like this, 10 to the power 6. So then that is 10 to the power 6 multiplied by cubic root is 1/3, and then that's again 10 to the power 2, or 100. The final one, which is an easy one, any number any number raised to the power 0, so that means it could be 525 raised to the power 0, that's 1. You could have like 23 raised to the power 0, that's 1. Unity. You can have an extremely large number, but still it's raised to the power 0. The answer would be simply 1. So I have two examples. As mentioned here, exponent rules are important when simplifying numbers involving scientific notations. So let's try to do the first example over here. You can see if you look at the numerator, the bases are the same. Again, the denominator, the bases are the same. So I'll basically add up all the exponents in the numerator. So I'll get 10 raised to the power minus 15 plus 4 minus 3, and then divide the entire thing by 10 raised to the power minus 5 plus 13, and then the numerator simplifies into, so minus 15 plus 4 minus 3, so that's minus 14, and in the denominator 10 raised to the power positive 8. Now further simplification means I can take this denominator with the exponent to the numerator, and the sign of the exponent will change. So I'll have 10 raised to the power 14 minus 8, giving me the final answer 10 raised to the power minus 22. So that's the simplified answer for example 1. So example 2, again we can see the first term, the base is 3 raised to the power 2. So keeping that base, I'm going to simplify that part. So 3 raised to the power 2, and that again has an exponent 6, and then we have 3 raised to the power 2. Again, the exponent of that entire thing is 2. Then division, 3 cubed raised to the power 2. So the first part I can write it in this way because we have the same base. I can write it as 6 minus 2. The division, I can do this. I can multiply and then take the reciprocal of this, like this. Okay, and then here 6 minus 2 is 4. So I have 3 raised to the power 2 multiplied by 4. And here in the denominator, multiplied by 1 over this number means basically this 3 cubed raised to the power 2. So then I can multiply the exponents. I'll have 3 raised to the power 8 divided by 3 raised to the power 6. You can see again the same base. So finally I can write this as 3, 8 minus 6, giving me 3 squared or 9. So that is the answer for this example. So this basically gives you some idea about exponent rules and how to apply them to simplify expressions, which is very important, as I told you, in physics. Another section that is important is solving simultaneous equations. So I'll explain this using these two examples. So the first example gives you two equations, 2x plus y equals 9, 3x minus y equals 1. So we have to solve them and find x and y. So I see a plus y and a minus y. So what I'll do is that I simply add these two equations together, and then I'll be eliminating the y variable. So I have 2x plus y equals 9, and then I have 3x minus y equals 1. I'm going to add the two equations, and then you'll see the plus y and the minus y will cancel out. On the left hand side I'll have 5x, on the right hand side I'll have 10. So I'll divide everything by 5, and then I'll have x equals 2. Now in order to find y, I will substitute this x value in one of these equations. So I'll use the second equation. So that means 3x minus y equals 1. So I'll substitute for x the 2 minus y equals 1. I'll have 6 minus y equals 1. So I'm going to move the y to the other side, plus y. So I'll add a plus y here. So then you can see these two cancels out. 6 equals 1 plus y, and then I'll remove the plus 1 to the other side by adding a minus y to both sides, and then these two will cancel out. So you can see then I get y equals 5. So those are the two solutions for this set of equations. You can always substitute these solutions back into the original equation, that is x equals 2 and y equals 5, and see if these are satisfied. So that's how you check whether your solutions are correct or incorrect. Let's go to the second examples. This is a little bit difficult than the first example. We can see there's a minus 2y and a plus 3y, but if you simply add the two equations, you are going to still see a y variable. So as a result, I'm going to do a different technique, but let me first number these two equations as equation 1 and 2. I'm going to multiply equation number 1 by 3. So multiply by 3 equation number 1, and then I'll get 12x minus 6y equals 12, and then I'll multiply equation number 2 by 2. So 2 multiplied by equation number 2, which will give me 10x plus 6y equals 32. Now I have these two equations, and now I'll see that there's a minus 6y and a plus 6y. So I'm going to use the method of elimination to simply get rid of the y variable here. So I'll add these two equations together, and then I'll have 22x. These two will cancel out, and then I'll have 44 over here, and then I'll divide the entire expression by 22, and then I'll get x equals 2 as one of the solutions, and then again I'm going to substitute x back in one of these equations. I'll use equation number 1 for example. So I have 4x minus 2y equals 4. Substituting 2 for x, I have minus 2y equals 4. Then 8 minus 2y equals 4. I'll add a plus y, 2y over here, and then I need to do the same thing on this side to get rid of the negative 2y. I have 8 equals 2y plus 4, and then I'll subtract 4 from this side, so I have to do it on the other side as well. So then these two will cancel out. So then further simplifying the equation as 2y equals 4, divide everything by 2, and I get y equals 2. Okay, so you get x equals 2 and y equals 2. I showed you step-by-step methods of simplifying these expressions, but you should practice these things, and you should actually try to do these things very quickly. Even skipping one or two of these steps would be fine, but in order to explain what actually happens, that's why I wanted to show all these steps. So again, you get x equals 2 and y equals 2. Substitute these solutions to the original equations and see if they satisfy the equations. If that's the case, then your solutions are correct. Solving quadratic equations is again something important, and I want to review that in this video. So if you are given a quadratic equation like this, ax squared plus bx plus c equals 0, the solutions, or sometimes we call them the roots of the quadratic equation, are given by this expression. We call this the quadratic formula. Inside the square root, you can see b squared minus 4ac. So this b, a, c, those are the coefficients of these terms in the quadratic equation. So this term b squared minus 4ac is called the discriminant. So this has a special name. It's called the discriminant. And depending on the positiveness, negativeness of the discriminant, your solutions will differ. For example, let me denote this by uppercase D. And if D is greater than 0, that is, D is a positive value, then you are going to get two solutions, two real distinct solutions. If D is equal to 0, then you get two solutions, but they are equal to one another. So two real solutions, but equal. Okay. And then the next case is when D is less than 0, that is, D has a negative value, then your solutions are imaginary, or we call the roots are imaginary. So this is something that you need to know when you're solving a quadratic equation, especially using the quadratic formula. So let's look at these examples. So here you have to identify what are the coefficients. So directly I can see the coefficient A equals just 1, coefficient B is equal to plus 5, and coefficient C is equal to minus 14. So then I'm going to make a substitution in this equation, in this formula, quadratic formula. I'll have minus 5 plus or minus square root of 5 squared, which is 25, minus 4 times 1 minus 14. And then the entire thing has to be divided by 2 times the coefficient of A, coefficient of the first term, which is A equals 1. And then when I simplify this, I'm going to get, let's see, minus 5, and then over here I have 25, and minus 4 multiplied by minus 14, I'm going to get 4 times 4, then it will be a plus value, 16, and I get 56, and then divide this entire thing by 2. So it's a matter of simplifying this expression, plus or minus square root. Here I'll get 1, and I'll get 81 here, and then divide by 2. So you should know the square root of 81, which is just 9. So I get x equals minus 5 plus 9 divided by 2, and x equals minus 5 minus 9 divided by 2. And you'll see the solutions for this quadratic equation is x equals x equals 2, and x equals there's going to be minus 14 divided by 2 minus 7. Okay, so those are the solutions for this quadratic equation in example number 1. Let's look at example number 2. So again, I'll identify the coefficients. Here in example number 2, A would be 2, then B is going to be minus 14. So remember to put the sign if there's a sign. And then C is again a negative number, minus 30. So I'm going to substitute these coefficients in the quadratic formula, and then I'll get x equals, there's a minus sign, minus 14, plus or minus, then inside the square root I'll have minus 14 squared, and minus 4 times A is 2, and then C is minus 13. And in the denominator, I have 2 times A, which is 2 times 2. So it's a matter of simplifying this. So if you simplify, you'll get plus 14, and inside the square root, you can do the calculation, and you'll see this, you are going to get like 300, which is a positive number, and then divide the entire thing by 4. Again, you can simplify this. You can take out, you can simplify the square root of 300 and then divide everything by 2. You get 7 plus or minus 5 square root of 3 divided by 2. So your answers would be x is 7 plus 5 square root of 3 over 2, and x is equal to 7 minus 5 square root of 3 over 2. So both these numbers are real, distinct numbers. So the solutions are real. There are two solutions. They are real and they are distinct, just like example number 1. So this should give you an idea about how to solve quadratic functions using the quadratic formula, which is shown here. Let's look at some geometric shapes that will be important for this course. So a circle, you need to identify what is the radius. It's the distance from the center of the circle to the edge, and the diameter is twice the radius. So diameter is usually denoted by d. So d is equal to twice the radius, where radius is represented by the lowercase r. Circumference is the length of the perimeter, what we call the perimeter, and that's given as 2 pi r. And also you can express the same thing in terms of diameter instead of using the radius, and then it will be pi times d. Area of a circle is pi r squared, where r stands for the radius. Again, you can represent this in terms of the diameter, then it would be pi d squared over 4. So these are important things that you have to remember, especially in this course. Now let's talk about the surface area of a sphere. Again, the radius of the sphere is given as r. In that case, it would be 4 pi r squared. Okay, again try to write this in terms of the diameter. Sometimes instead of giving the radius, one could give the diameter. So you should be able to write all these quantities in terms of radius and in terms of the diameter. The volume of a sphere is given as 4 over 3 pi r cubed. Always remember, when it comes to the volume, the radius varies as r cubed. If it's a surface area, the radius varies as r squared, because surface area is two-dimensional. So that means it's proportional to radius squared. However, volume, it's three-dimensional. You have a length, a width, and a height, 3 dimensions. As a result, radius to the power 3 or cubic. So that's an easy way to kind of distinguish areas versus volume. Now let's talk about a cylinder. The area of a cylinder can be broken down into this curved surface and these top and bottom caps. So the total area would be the area of the two caps, which is 2. The cap is basically a circle, so I have 2 times pi r squared. R is the radius. You can see h is the height of the cylinder, plus now the area of this curved surface. So that is written as 2 pi r times h. Okay, so that gives you the surface area of a cylinder. Now the volume of a cylinder is simply the area of the circle multiplied by the height. So that is pi r squared times h. This gives you the volume of the cylinder. So these are some of the important geometric shapes that you need to know, especially how to find the area, how to find the volume of these geometric objects. And that's, again, as I told you, will be important in this course. Okay, we will continue geometric shapes. There are 5 types of angles that you need to know. They are right angles, straight angles, acute angles, obtuse angles, and reflex angles. So a right angle, obviously, something like this. There's a 90-degree angle, and that's what we call a right angle. A straight angle is like a straight line. Let's say that there's point O, and then you measure the angle like that, and that will give you 180 degree of an angle, and that's a straight angle. An acute angle is an angle that is less than 90 degrees. So something like this. So let's say this angle, like it could be like 30 degrees. So it's less than 90 degrees. Usually we denote the angle by the Greek letter theta. So in this case, generally I can represent it as theta less than 90 degrees. And that's called an acute angle. And then the fourth one is called the obtuse angle, that is larger than 90 degrees. So something like this. This is O, and this angle over here. Let me again denote that by the Greek letter theta, and whenever theta is larger than 90 degrees, we call that an obtuse angle. And the fifth angle that you need to know is called the reflex angle. So again, something like this. But now instead of looking at this angle, we look at this angle. That's our theta. So here, theta is larger than or greater than 180 degrees. Okay, so that's when we call that's an angle we call a reflex angle. So these are the 5 types of angles that you need to know. Now let's look at a triangle. Especially finding the the perimeter of a triangle should be straightforward, but sometimes people have difficulty in finding the area of triangle. So here I have a right angle triangle. Let's say that this is obviously a right angle. You can see that. So the general formula for finding the area of a triangle is 1/2 multiplied by the base of the triangle multiplied by the perpendicular height drawn to the base from a vertex. A vertex is one of these points. Like any of these points, we can call them vertices, or like singular form is vertex. So that's a vertex. Okay, so perpendicular height, or simply 1/2 base multiplied by height. So if we use that for this 90-degree angle, the right angle triangle, we get 1/2 base is given as b, and the vertical height is this one, h. Again, if you have a triangle like this, identify the base, that is this one, and the vertical height is this height. Okay, so again for this this is for this triangle, and the expression here, it would be the same, 1/2 b times h. If you have a triangle like this, you can still identify the base. So you have 1/2 b, and the height, vertical height, how do you find the perpendicular height? Extend this line from the base and then draw a perpendicular from the vertex to the line that intersects the perpendicular line, and you'll see that height is the same height, h. So basically this is the equation that you need to understand when finding the area of a triangle, any type of triangle, 1/2 base times the perpendicular height. In this section, we are going to talk about proportionalities and ratios. Proportionalities are important when we talk about relations. So there are 3 relations given here. Each one of these will have something called an independent variable and a dependent variable. So the first 2 relations are direct proportionalities. So that means when one variable is increasing, the other variable is also increasing. When one variable is decreasing, the other variable is decreasing. This symbol over here, it looks like alpha. So that's what we call the proportionality symbol. So the first relation and the second relation are direct proportionalities between the 2 variables, but the third one is an inverse proportionality between the 2 variables. So that means when one variable is increasing, the other variable is decreasing, and vice versa. So these are the 2 types of proportionalities that we'll see: direct proportionalities and inverse proportionalities. So we can combine these 3 relations and write this expression. Now, if we want to convert this to an equation, what we need to do is that we need to multiply the relation by something called a proportionality constant. Here it's represented by k. Now, when we multiply that, we get equation number 1. Now, suppose x3 variable is doubled. So that means in the denominator you can see a 2 here, and as a result we end up with a new equation, and that's why I call it equation number 2. Now we can use equation 1 and equation 2 to find the ratio between y and y prime, because this is something that we usually find in physics, finding the ratios, finding the proportionalities, things like that. So the ratio can be written like this: y, this colon-like symbol, y prime, or we can write it like y to y prime, or even like a fraction, y over y prime. So these are 3 ways of representing a ratio between 2 variables. So in this case, let's look at this example, equation number 1 and equation number 2. If we want to find the ratio between y and y prime, I'm going to write it like this. So from equation number 1, y is k x1 x2 over x3, and y prime is k x1 x2 over 2 times x3. So you can see the common terms. If I simplify it further, removing the common terms, I will have 1/1 like that. So that means y over y prime can be written as 1 over 1/2. So in other words, it's like 2. So finally, I can write y with the ratio between y and y prime as 2 to 1. Okay, so this simplification, this identifying the proportionality, writing the ratios, simplifying the ratios is very important in this course. So that's why I want to review it like this. Okay, let's try to do these 2 examples that are related to proportionalities and ratios. So in the first example, you are supposed to find the ratio of P1 to P2 to P3, provided you are given P1 equals I squared R1, P2 equals I squared R2, and P3 equals I squared R3. You can see that I squared is common in all these three equations. So P1 to P2 to P3 can be written in this way: P1 to P2 to P3, and then that's equal to I squared R1 to I squared R2 to I squared R3. So I squared is common, so then what I can do is that I can remove that I squared from the entire expression, and then I'll have R1 to R2 to R3. So that's one way of writing it. Another way to express the same relationship is use like fractions. So I can write the same thing as P1 over P2 is equal to R1 over R2. And also I can write P2 to P3 is equal to R2 to R3. And if I want to, I can write the other one as well. P3 over P1 is equal to R3 over R1. So it's the same way. So this representation over here is identical to this representation. It gives you the same mathematical idea. Okay. The second example, find the ratio between the original volume to new volume if the radius of a sphere is tripled. So you should know the general formula for the volume of a sphere where the radius is r. So that's given as 4 over 3 pi r cubed. So let me call this the original volume. So the new volume, according to the data given, is equal to when you triple the radius of the original sphere. So that means 4 over 3 pi. Instead of r, now I need to put 3 times r and cube the entire thing. And as a result, you can see there's a factor of 3 to the power 3, which is 27, coming from this expression. So I have 27 times 4 over 3 pi r cubed. So in terms of the ratio, I can write this as V original to V new as 4 over 3 pi r cubed to 27 4 over 3 pi r cubed. Now 4 over 3 pi r cubed is common, so we can remove that and we can simplify the ratio as 1 to 27. Okay, so this is one way of writing this. The other way is as a ratio, just like in the example 1, V original over V new. I can write this thing 4 over 3 pi r cubed divided by 27 4 over 3 pi r cubed, and then you can see these two terms cancels out, so I have this 1 over 27 ratio. So it's mathematically this way of getting the relationship. The final outcome is identical to this way of representing it. So these are two examples to give you an idea about how to deal with proportionalities and ratios. In this part, we are going to look at logarithmic rules and logarithmic functions. So there are two forms of logarithmic functions, the base 10 logarithms and base e logarithms. Sometimes base e logarithms are called natural logarithms, where e stands for E has a numerical value of 2.718. So these are some important rules that you need to identify. So if there's a product and you take the logarithm of that product, that's equal to the sum of the logarithms. So for example, if you have something like this, ln 25 times 3, we can break it into ln 25 plus ln 3. Okay, this symbol, you can see these two parallel lines, that gives you the modulus. It basically tells you just take the magnitude of that number. So for example, if you take the modulus of, let's say, minus 9, negative 9, that's equal to 9. Okay, that, like that. So in this rule is the ratio. If you take the logarithm of a ratio, that's equals to the different of the separate logarithm. So again, 25 over 3, if you see something like this, you can represent it as ln 25 minus ln 3. Now this one, the power rule, a very important one. So let's say you have 10 raised to the power 3, then this can be represented as, simply expressed as 3 times ln 10. Another one, important one, is, let's say you have ln 1 over 4. So you can rewrite this 1 over 4. You can move the 4 to the numerator, and then its exponent becomes a negative value, like that. And then you can apply the power rule, minus 1 ln 4, like that. So these are some rules that you should familiarize in order to do problems related to exponents and exponential functions or logarithmic functions. So let's try to solve this problem. So we need to solve for t. So what I can see that there's an exponential function here. I'm going to in order to remove the exponential function, I need to take the logarithms. This is a base e function, an exponent, so I'll take the natural logarithms on both sides. So ln 1 over 4 is equal to ln e to the power minus 5t. So then I can simplify this as minus 1 ln 4, as I showed here, equals, when so ln is the anti-operation of exponent, so then this becomes minus 5t. So you can see the minus sign simply falls off from the equation, and then I can solve for t, which is ln 4 divided by 5. So that's how you simplify this particular equation to solve for the variable t. Okay, in this section we are going to briefly talk about the number line and the xy coordinate plane. So the number line is a one-dimensional system to measure position relative to a reference point. So the reference point here is 0, as you can see. Anything to the right of the 0, that's considered positive numbers, and to the left they are considered negative numbers. So if you move to a position like this relative to the origin, then we call it like, plus 3 or 3 units to the right. And if you move to a position like this, that is minus 2, we can say 2 units to the left. So that's how we use a number line. It's one dimension. One side, usually the right hand side, is considered positive. Left hand side is considered negative. When you put two number lines perpendicular to one another and construct a two-dimensional grid, that's when we call an xy coordinate plane. So remember, simply a number line is one-dimensional. in the case of the xy coordinate plane, that is two-dimensional. So that means you need two coordinates to specify a position. We can define, when we have the xy coordinate plane, we can define four quadrants. So this is the first quadrant, this is the second quadrant, third quadrant, and the fourth quadrant. And in each of these quadrants relative to the origin, we can represent a particular position. So for example, over here, how do we define that position relative to the origin? First we write its x coordinate, which is 4, and its y coordinate is also 4. If we think about a point in the second quadrant, the x coordinate is minus 6, whereas the y coordinate is 1. A point like this in the third quadrant, x coordinate is minus 3 and the y coordinate is minus 2. And in the fourth quadrant, if we consider a point like this, its x coordinate is 2 and its y coordinate is minus 4. So that's how we represent positions in the xy plane relative to the origin. Since it's two-dimensional, you need 2 points to define, 2 coordinates to define a position, but on just a one-dimensional number line, you just need 1 coordinate to specify the position. In this section, we are going to talk about a very important theorem in math that is extensively used in physics. That's called the Pythagorean Theorem. So we need a right angle triangle to discuss the Pythagorean Theorem, and just for simplicity, I'm going to use a right angle triangle in the first quadrant. So I'm going to select the triangle. So this is one side, you need 4 units. The other side is 3 units, and then I have the third side like that. And then the Pythagorean theorem talks about the areas that are made by these sides. So here I have this side, you can see it's 3 units. The area of squares, so if I construct a square over here, so this area, so let me call this side A, and let me call this side B, and this side C. So the area of this square is A squared, and if I construct a square where the side is B, then it would look like this. Okay, so this area is B squared, and then I consider this side and a square with sides that is C. Like that. Okay, and then this area is C squared. So Pythagorean said that there's a relationship between these areas. He said that this C squared is always equal to A squared plus B squared. So this is what we call Pythagorean theorem. It's a very important theorem that you guys need to really understand and really use to solve certain expressions that will come in physics. So for example, if you want to solve for C, you can simply take the square root of A squared plus B squared, and let's say you want to find the side B, then you can solve for B squared, C squared minus A squared, and then find B. Take simply the square root of C squared minus A squared. Okay, and if you want to find A, again A squared, you can write it in terms of C squared minus B squared, and A is square root of C squared minus B squared. So that means if you know 2 sides, you can simply get the other side, okay, using Pythagorean theorem. and then that's very important. So for example, let's say you have a right angle triangle like this, and let's say this is in our example, this is I told you that that's 4 units, and this is 3 units. You want to find the length of this longer side. How do you do that? We can use Pythagorean theorem. I identify 3 as A and 4 as B, and I need to find C. I simply use this Pythagorean theorem. So C squared is equal to A squared, which is 3 squared, and B squared, which is 4 squared. And then if you see, I can use this to find C, that is the square root of this entire thing. 3 squared plus 4 squared, which is square root of 25, and the answer is 5. Okay, so that's how you use Pythagorean theorem to find an unknown side of a given right angle triangle. If the other two sides are given, you can use this very quickly to find the third side, the dimension, the length of that third side. So this is Pythagorean theorem. Here we are going to study radians and degrees, two important ways of quantifying angles. Also, these are important when we discuss trigonometric functions, and also you should know how to convert between radians and degrees. So let's start by defining what is a radian. Here you can see I have a circle, and I'll define the center of that circle, and let's assume that the radius is r. What I'm going to do is that I'm going to take an arc length that is equal to the length of the radius of this circle. So let's say that's the arc length, the length of the arc length. So this is arc length. And its length is equal to the radius. And in that case, you can see this arc length will subtend an angle at the center of the circle. This angle is what we define as a radian. So the size of that angle is called 1 radian. In terms of degrees, 1 radian is equal to 57.3 degrees. Okay, so a radian is the angle subtended at the center of the circle when arc length is the same as the radius of the circle. Okay, so keep that in mind. That's very, very important. Now, how do we generalize this to a different angle, to an arbitrary angle? So again, let me draw a circle like that. And then this is the center of that circle. And now I have an angle like this. So this is the arc length. And let me call that arc length as S. Now what I'm going to do is that this is the radius. I'm going to break this arc length into in terms of the radius, of the circle. So there could be one radius over here, and there's another radius here, and then part of the this could be another fraction of a radius. So what I need to do is that I need to get that arc length and then divide that arc length by the radius, and then this ratio is equal to the angle subtended at the center in radians. This is a very important equation, so we can rewrite this equation as S equals R theta, where theta is measured in radians. So keep this in mind. This is going to be very, very important in the coming chapters when we discuss physics. Okay, so that's how you define the radius. 1 radian is equal to 57.3 degrees, and then this is a general expression to find the angle in terms of radius. You are given the arc length, you already know the radius, and then using this equation you can find the angle subtended at the center in terms of radians. Now another important, so this is the first one that is important, definition of the radius, radian, and then this is this very important relationship, and the third one I'll show it over here. What is the angle subtended by the circumference of a circle? So that's another important thing. So you have a circle like this, okay, and then this is the center, the circumference. So it's now the arc length is a special value. It's the entire perimeter of the circle. C is equal to 2 pi r, that is the circumference, but in this case the arc length is equal to c, or 2 pi r, the circumference. So what is the angle in terms of radians for that particular situation? We can simply use this relationship. For s, I'm going to substitute 2 pi r and then divide by r cancels out. So theta in this case is 2 pi radians. So the circumference subtends an angle 2 pi radians at the center. We already know that angle in terms of degrees, which is 360 degrees. So now we have another relationship between radians and degrees that can be used to convert between these two units. That is 2 pi radians is equal to 360 degrees. So this is another important relationship that you should know. These are important also when we study trigonometric functions, or sometimes they are called trigonometric ratios. So let's do some examples related to radians and degrees. Here what we need is to convert these degree values to their radian values. So I'll use the previously established relationship between radians and degrees. If you recall, I said 2 pi radians is equal to 360 degrees. So in other words, 1 radian is equal to 360 degrees divided by 2 pi, or we can simplify this and say that's 180 degrees over pi. So 1 radian is 180 degrees over pi. And another important relationship is 1 degree is equal to pi over 180 radians. Okay, so I basically inverted this where I solve for 1 degree. Here you can see it's solved for 1 radian, but this is for 1 degree. So I'm going to use this in order to convert these degree values into their radian values. So 10 degrees, I can write this as 10 times 1 degree. Okay, and for 1 degree I'm going to make the substitution, 10 times pi over 180 radians, and then you can see the answer is pi over 18 radians. Similarly, I can do 30 degrees. 30 times 1 degree equals 30 multiplied, instead of 1 degree, I'm going to substitute pi over 180 radians. And then the answer over here is pi over 6 radians. And then 60 degrees, again 60 times 1 degree, 60 multiplied by pi over 180 radians, and you can see this is pi, when you simplify this, pi over 3 radians. And then final one, 120 degrees, again I can break this into 120 multiplied by 1 degree, and I'll substitute for 1 degree pi over 180 radians, like that. And then further simplification will give me the answer 2 pi over 3 radians. So this is how you convert from degrees to radians, and this is very important. In the coming chapters you will see we are going to use this very frequently, and this whole idea of converting from one unit to another unit is called unit conversion, and in a separate video I will again discuss some of these examples. Okay, so now let's go to the next one. Here we are doing the reverse, that is, we are given the radian values and we need to find the degree values. So in this case, I'm going to use that 1 radian is equal to 180 degrees over pi. So this is the conversion factor. We usually call this the conversion factor to make the conversion from radians to degrees. So the first one, 5 pi over 6 radians, I can rewrite this as 5 pi over 6 times 1 radian, and then for 1 radian I can substitute 180 over pi. 5 pi over 6 times 180 degrees over pi, and when you simplify this you will get the angle as 150 degrees. So that's 150 degrees. And then the other one, 7 pi over 8, 7 pi over 8 radians, again I can break this into 7 pi over 8 times 1 radian, and I'll substitute for that 1 radian 180 degrees over pi, and then simplify this and you should get the answer as 157.5 degrees. Yes, that's the answer for the second example. The third one is 3 pi over 2 radians, and again 3 pi over 2 multiplied by 1 radian. So now I guess you get the idea on how to do these calculations. 180 over pi. So then here you are going to get 270 degrees as your answer. Okay, and then the last one, 9 pi over 10 radians. So that means again 9 pi over 10 multiplied by 1 radian. I'm substituting for that 1 radian, 180 degrees over pi, and then when you simplify this you can calculate, use a calculator and find the answer, but I get 162 degrees for the answer. So that's how you convert from radians to degrees. So this is what we used. It's usually called the conversion factor, and we used a similar conversion factor over here when we converted from degrees to radians. So that's basically it for radians and degrees. In this section, we are going to talk about trigonometric functions. So let me first define how we measure angles. We always measure an angle relative to the positive x-axis. So this is our positive x-axis. Okay, and that's considered 0 degrees, and we always go counterclockwise direction, and that's considered the positive orientation. So if it's 0 here, then this is considered 90 degrees, and this is considered 180 degrees. This is 270 degrees, and when you come back to the same original position, you have completed 360 degrees. Okay, now you can express the same thing in terms of radians. 0 radians. Over here it's pi over 2 radians. Over here it's pi radians. Over here it's 3 pi over 2 radians, and then coming back to the original position, you have completed one whole circle, so that is 2 pi. So if you have any angle in the first quadrant, you should know that it should be between 0 degrees and 90 degrees. In the second quadrant, if it's in the second quadrant, then the angle should be between 90 degrees and 180. In the third quadrant, 180 degrees and 270 degrees. So like that, okay? So again, an important convention, counterclockwise angles are considered positive. Clockwise angles, they are considered negative angles. So for example, let's say that in the first quadrant I am measuring an angle, and let me call this 30 degrees from the positive x-axis, and you can see it's a positive number. Now if I measure the same angle, let's say relative to the positive x-axis in the clockwise direction, that's going to be negative 30 degrees. Okay, it's not positive 30 degrees, it's negative 30 degrees. So that's the important thing that I want to discuss. Depending on the quadrants, you should know how to identify the range of the angle, and depending on the orientation you measure angles, whether it could be counterclockwise orientation or clockwise orientation, the angle could be positive or negative. So keep that in mind, that's going to be very important. Now let's look at just the first quadrant, and what I'm going to do is that I'm going to draw a right angle triangle, ABC right angle triangle, in the first quadrant, like this. And then you can see why this is a right angle triangle, because you have a 90 degree angle. And I'm going to name it, let's say A, B, and C. Okay, and then let me define this angle. You can see positive x-axis, this is the first quadrant. So this angle, this is 30 degrees. And you can see from the geometry, this theta has to be less than 90 degrees, and it should be greater than 0 degrees because it's in the first quadrant. Now relative to this angle theta, I can define BC, the side BC, as the opposite side. So that's going to be the opposite side. And then relative to theta, AC is called the adjacent side. And then AB is called the hypotenuse. Now using these three sides, we can define trigonometric functions. So the first trigonometric function that I'm going to define is called sine theta. So it's defined as the opposite side divided by the hypotenuse. So opposite is BC, and you can see hypotenuse is AB. Let me call this equation number 1. The next one is cosine theta. So cosine theta is defined as the adjacent over hypotenuse. Adjacent is AC over hypotenuse is AB. And the third one that I'm going to define is called the tangent theta, and that's defined as the opposite over the adjacent. The opposite is BC and the adjacent is AC. So let me call that equation number 3. Now what I'm going to do is I'm going to divide equation 1 by equation 2 like this. So that means I have equation 1 sine theta. So equation 1 over 2 means sine theta over cosine theta. But sine theta is this ratio BC over AB. And then cosine theta is the ratio AC over AB. You can see these AB's in the denominator of the first term, and in the denominator in the second term, they cancels out, and then you get BC over AC. So from equation number 3, you can see BC over AC is nothing but tangent theta. So then we get something called a trigonometric identity. So that means tangent theta can be written as sine theta over cosine theta. So this is a very important trigonometric identity. You should keep this in mind. Now let's square equation number 1 and equation number 2. So if we square equation number 1, I'm going to get sine squared theta, that is equal to BC squared over AB squared. And then when I square equation number 2, I'll get cosine squared theta is equal to AC squared plus AB squared. Now I'm going to add these two together. So 1 squared plus 2 squared, and that's going to give me, on the left hand side, I'll get sine squared theta plus cosine squared theta equals BC squared over AB squared plus AC squared over AB squared. You can see there's a common denominator, AB squared, and in the numerator I can rearrange this as AC squared plus BC squared. Now what is AC squared plus BC squared? If you look at this right angle triangle, AC is the adjacent side, BC is the opposite side. So the numerator over here is basically the square of the adjacent side plus the square of the opposite side. So simply that gives you a way to apply Pythagorean theorem to this right angle triangle. So if you apply Pythagorean theorem, then you will get to this right angle triangle ABC, you will get the square of the hypotenuse is equal to the sum of the squares of the other two sides, that is AC squared plus BC squared. So that comes from the Pythagorean Theorem, which we discussed earlier. So I'm going to apply Pythagorean Theorem, and then you'll see this would be AB squared. Okay, and then you are simply going to get AB squared in the numerator, AB squared in the denominator, and simply it's equal to 1. So this is another very important trigonometric identity where you get sine squared theta plus cosine squared theta is equal to 1. Okay, let's look at some trigonometric identities that will be useful in our course. Now, these identities, when you are using them in solving problems, you don't need to derive them or prove them. You can just simply use them. So let's consider if theta is measured in, where theta is an angle, it's measured in either radians or degrees. Then the following identities are useful for physics problem solving. So the first set of identities, sine 2 theta equals 2 sine theta cosine theta. Okay, so as an example, let's say you have sine 60 degrees. You can expand this as 2 sine 30 degrees multiplied by cosine 30 degrees. Sometimes it's called the half angle identity because you have 2 theta here and thetas here. And now the corresponding cosine to theta can be written as cosine squared theta minus sine squared theta. Again, as an example, you can think about, let's say, cosine 120 degrees. So that's the same as saying cosine squared 60 degrees minus sine squared 60 degrees. Okay, so this is the first set of identities. The second set of identities that will be important are like sine 90 minus theta. So if you have sine 90 minus theta equals cosine theta, and then cosine 90 minus theta, that's equal to sine theta. So in the xy coordinate system, these two equations or identities are related to the first quadrant. First quadrant. The third set of identities that I want to discuss are these. Sine 180 degrees minus theta equals sine theta. Then cosine 180 degrees minus theta equals minus cosine theta. So keep in mind the sign change, okay? Cosine minus cosine theta. And then the tangent 180 degrees minus theta equals minus tangent theta. So these are relevant for the second quadrant. If you think about again the xy coordinate system, these are relevant in the second quadrant. Especially this one will be very important when we talk about graphing. So that will be the next section that I'm going to talk about after trigonometric functions, graphing. And in graphing, we usually need to find something called the slope of a curve, rise over run. And when we do that, you'll see this trigonometric identity will be very important. The final set that I want to talk is identities in the fourth quadrant. So sine minus theta equals minus sine theta. So minus theta here is the angle measured in the clockwise direction. As I told you earlier, when you measure an angle, it could be degrees or theta, it doesn't matter. If you measure the angle counterclockwise, it is positive, but clockwise, that's negative. So this angle is measured clockwise and it goes to the fourth quadrant. The next one, cosine minus theta, so that's going to be cosine theta. And then finally, tangent minus theta is equal to minus tangent theta. So these are relevant for the fourth quadrant in the xy plane. Remember, for this theta, you can have radians or degrees, it doesn't matter. So, I mean, as an example, if you think about sine 90 minus theta, you can have something, let's say, sine, this is an example, 90 minus 30 degrees. Okay? And according to this, that is equal to cosine 30 degrees, right? Because this theta is this 30 over here. And then you'll have sine 60, because 90 minus 30 on the left hand side, that is 60. So sine 60 is equal to cosine 30 degrees. So you can use a calculator and verify this if you want to do that. As an example, for this set of identities, I can have sine, let's say 180 minus 20 degrees, where theta is this 20, and that is equal to sine 20 degrees. So 180 minus 20 is sine 160 degrees equals sine 20 degrees. Okay, so that's an example for this third set of equations, identities. And for the final set of identities, I can have this as the example. Let's say cosine minus 45 degrees is equal to cosine 45 degrees. Or you can have tangent minus 60 degrees is equal to minus tangent 60 degrees. So again, remember, you can verify these using the calculator, and these are all valid for theta, when theta is measured in radians, as well as when it's measured in degrees. Now let's look into graphing some of the trigonometric functions, especially sine theta and cosine theta. So here you can see a table where I have listed angles in degrees and their corresponding angle in radians, and the numerical value for the sine theta, that is the sine theta value. And pretty much what we have is a function like this, y equals sine theta. So sine theta goes to the y-axis, which is going to be our dependent variable, and then theta is the independent variable. And let's consider it's measured in degrees over here. So if we plot these values, you will see that you're going to get a curve like this. And you put the data points, and then you can connect the data points, and then you'll see something like this. So this is what we call a sinusoidal function. It's called a sinusoidal function because it looks, it pretty much looks like a sine function. So that's why it's called a sinusoidal function. So this is an example for a sinusoidal function. So here you have 0, and then at this highest point it corresponds to 1, and then the angle over there is 90 degrees. And here the 0 value, that corresponds to 180 degrees. And then this maximum value, however, that's in the negative direction, that maximum value corresponds to -1, and the angle over at that moment is 270 degrees. And then over here you have 360 degrees. So this is what we call a sine wave, a sine function. Very important. It's a very important model when we discuss oscillatory motion, oscillatory motion, simple harmonic motion. Then you will see this function will be very important. So if we look at the maximum value and the minimum value for a sine function, that's given as the maximum value sine function can obtain, you can see that's +1. The minimum value the sine function can obtain is -1. Now this height over here from this x-axis to the maximum displacement, we have a special name for that. You will learn this later on. It's called the amplitude. And similarly on this side, we have the same amplitude. Maximum displacement from the equilibrium position or the equilibrium line. So this separation, that's amplitude. Okay, so I hope this gives you some basic idea about the sine function. Now let's look at the cosine function. It's going to be the same kind of process. I have again listed a table. You can see the theta values in degrees, their corresponding values in radians. And then what we can do is we substitute for this angle using a calculator, and then we can get the numerical value for cosine theta. So again, y equals cosine theta. So that's the function where theta is the independent variable and y or cosine theta is the dependent variable. And again, I'll use the angle in terms of degrees. And then here when you plot this curve, you can see at 0 angle, cosine theta is 1. So that's somewhere here. That's +1. And then you can see at 90 degrees, cosine value is 0. And then at 180 degrees, it's -1. And 270, it's 0. 360, it's 1. So you can see the profile is different from y sine theta function. So it's going to look like this. It's going to decrease and then at 90 degrees it will be 0, and then at 180 degrees it will reach a maximum value in the opposite direction. So that is like -1. And then, so here 90 degrees, over here it will be 180 degrees, and then it's gonna go like this, and when it crosses the x-axis again, that would correspond to an angle of 270 degrees, and then it will reach to its maximum value over here, and that corresponds to 360 degrees. So you can see, I mean, this is just a sketch, it's not perfect, but I believe you get the idea. Again, what you can see is that the cosine function also has a maximum value and a minimum value. Cosine theta, the maximum possible value is 1. The minimum value it can take is -1. Cosine theta, sine theta, these periodically varying functions are called sinusoidal functions. So again, just to remind you, this separation is what we call the amplitude. That is the maximum displacement from the equilibrium position, or in this case, from the horizontal x-axis. Okay, so these are the only two functions that I'm going to graph for trigonometric functions, that is y equals sine theta and y equals cosine theta. You should have some idea about at least identifying these functions. When you see a function like this, you should very quickly identify that this has to be a trigonometric function. It's a sinusoidal function, like that. So that's very important. Okay, let's wrap up this section by doing two examples. The first example, according to the given right angle triangle, so ABC triangle is right angle triangle, sine theta is 3/5, determine cosine theta and tangent theta. So you are given sine theta as 3/5. So then the first thing that you have to remember, the definition of sine theta, right? So sine theta is what? It's basically the opposite side of the right angle triangle divided by the hypotenuse. Okay, so now let's go to the right angle triangle, and relative to the angle, let's try to identify what is opposite, what is the hypotenuse, what is the adjacent. Opposite to the angle, that is by definition the opposite side. The longest side is what we call the hypotenuse. And then adjacent to the angle other than the hypotenuse is the adjacent. So that means we are given sine theta is equal to 3/5. So that means opposite has to be 3 units, and hypotenuse, it has to be 5 units. So this is 3 and this is 5. We have a right angle triangle. Two sides are given, are known. We need to find the third side in order to find the cosine value and the tangent value of this angle. So how do we find this AC length? We can use Pythagorean theorem. According to Pythagorean theorem, we have AB squared equals AC squared plus BC squared. Okay, so then what we need to do is we need to solve for AC. So I can rearrange this. AC squared equals AB squared minus BC squared. And AC is the square root of AB squared minus BC squared. So I'll make the substitution now. AB is 5, so I have 5 squared. BC is 3, so I have 3 squared. And that's the square root of that entire thing is equal to AC. So AC is 25 minus 9, so that is 16. So I'll have square root of 16, which is 4 units. So AC is going to be 4 units. So now we know the hypotenuse, we know the opposite side, and we know the adjacent side in terms of their lengths. Now we can find the cosine theta as asked in the question. So cosine theta is the adjacent divided by the hypotenuse, which is 4 over 5. Okay, so this is given in our question, but this is one that we actually figured out. And then the other one, tangent theta, by definition that's opposite side divided by the adjacent side. And opposite is 3, adjacent is 4. So tangent theta is 3 over 4. So that's how you figure out the trigonometric functions in this particular example. Now, a very important thing to note here, I will talk about this when I discuss vectors, but still there's something important that you should know. So let me use a different color to explain this. So if we have a right angle triangle, let's say that's our right angle triangle. And then this is the angle theta. And let's say this length is given as L. This is L. And we want to figure out this side, let's call it Y. And this side, it's X. How are we going to do that? We can simply use the definitions of sine theta and cosine theta to do this. We need to identify that L stands for the hypotenuse, this Y stands for the opposite side, and this X stands for the adjacent side relative to this angle. That's the first thing that you need to identify. And then apply sine theta, the definition of sine theta, opposite over hypotenuse, Y over L. And then you can see the other one, cosine theta. By definition, that's the adjacent over hypotenuse. Adjacent, as we identified, that's X over L. So now you can find Y, X and Y in terms of L and theta. Simply solve for Y. You can see Y equals L sine theta, and then X is equal to L cosine theta. So you'll see later on in the vector review as well as during the course, you'll see this sine component and the cosine component. How to find the sine component, cosine component would be extremely important. So keep this in mind because this is very, very important. Okay, so this part is important. Now let's go to the second example. So this is the second example. Again, it uses geometry and some basic trigonometry that we discussed. Find the length AC, length of side AC of the given triangle ABC. So you can see ABC triangle. We need to find this distance. So let me call that L. We need to find a value for L. If you look carefully at this triangle, you can see sides AB and BC are equal. When two sides of a triangle are equal, we say that's an isosceles triangle. So that's an isosceles triangle. And another important thing in such a triangle is these adjacent angles are equal to one another. So I'll represent those two angles by theta. So this is theta. This is also theta because it's an isosceles triangle. This length equals this length. And then we also know a very fundamental geometric rule, principle, saying that the sum of the two opposite angles, so sum of the two opposite angles, that means these two angles, is equal to the exterior angle. So that's the exterior angle. So that means sum of these two angles, which means 2 theta, is equal to the exterior angle 60 degrees, and from there we can find theta is equal to 30 degrees. So this angle is 30 degrees and this angle, that's also 30 degrees. Now the objective is to find this length AC. What I'm going to do now is to draw a perpendicular line from point B to AC. So this is a perpendicular drawn to AC, and this line actually bisects this angle. So that means this angle equals this angle. So we have this angle over here equals this angle. The sides BC is 10, and that's the same as the side AB, which is also 10. We have the perpendicular line common to both of these triangles. As a result, this length AC is divided in half by this perpendicular line, and we have two congruent triangles. So let me call this point D over here, and then we have ABD and CBD triangles which are congruent to one another. Triangle ABD and triangle CBD are congruent. So that means their angles are the same, their sides are the same. As a result, I can write this length AC in terms of AD. So you can see AC can be broken down into AD plus DC. But since these two smaller triangles are congruent, I have AD equals DC. So that means I can rewrite the right hand side as AD plus AD equals 2AD. So instead of finding AC, what I can do is that I can find AD and multiply that value by 2. So how do I find AD? What is AD? AD is this side of this smaller ABD triangle. And the important thing is that that's a right angle triangle. So let me highlight that right angle triangle so it's more clear. So this is that right angle triangle. You can see this is the 90-degree angle. This 10 or AB is what we call the hypotenuse. And then this side, which is opposite to the angle theta, is what we call the opposite by definition. And then this has to be the adjacent side. So now I can go ahead and define the trigonometric functions that we discussed earlier. Actually, I'm going to define cosine of the angle, cosine theta. So if you look, cosine theta is equal to adjacent divided by the hypotenuse. Adjacent is AD and hypotenuse is AB. Now I can substitute the values. Theta is 30 degrees, so cosine 30 degrees is equal to AD. That is what I need to solve for this problem, and AB is 10 units. So you can see AD is simply 10 times cosine 30 degrees. Now from this equation, let me call that equation number 1. From 1, I get AC is equal to 2 times AD, which is 2 times 10 cosine 30 degrees. And now you can use a calculator to find the answer. You'll see that the answer is 17.32 units. So that's how you do this example. Here we use some basic rules in geometry as well as the definition of one trigonometric function, namely the definition of the cosine function. In this section, we are going to talk about graphing. I will discuss two types of graphs, linear graphs and nonlinear graphs. Now, graphs are plotted on an XY coordinate system. So here we have two perpendicular axes. The horizontal axis is usually called the x-axis, that's the positive x direction to the right. And then the vertical axis, that's called the y-axis. In this direction, the upward direction, that's called the positive y direction. The two axes intersect at this point, and that's our origin, the point 0 or 0, 0 coordinate. Now, what is a linear equation or a linear relationship? Let's say that we have y and x variables. Now, if you recall, x variable is also known as the independent variable. And the y variable is called as the dependent variable. So if we have a relationship between this independent variable and the dependent variable, like in this form, you can see x and y are directly proportional to one another. I discussed this symbol in a previous section. They are directly proportional, x and y, and you can see their exponents are 1. So this sort of a relationship is called a linear relationship. Now I can multiply this by a proportionality constant, let me call that m, and then the relationship becomes an equation, y equals mx. So we have this type of a linear equation or a linear relationship, or we can have it in this way, y proportional to minus x. Instead of plus x, now we have minus x. So again, I can multiply the relationship by a proportionality constant, and then I will have this equation. I'll call that proportionality constant m prime. Okay. Now I will discuss y equals minus mx later. However, let's focus on y equals mx. the y equals mx equation, its graph on this xy coordinate system would look like this. It's a straight line that goes through the origin in this way. And that's what we call y equals mx line or the graph. Now, another important thing is defining the slope or the gradient of a line. That is very important. Again, we'll consider our xy coordinate system. And then I'll draw our y equals mx line that goes through the origin like this, y equals mx. The slope or the gradient is defined in this way. The slope is defined as the rate of change of y variable with respect to x variable. That is how we define the slope of a straight line. So in terms of the x, y variables, slope can be defined as delta y over delta x. So what is delta x and what is delta y? If we look at this line y equals mx, let's first define 2 points on the line. Let me call one point as a, x1, comma, y1, and the other point, let me call it b, x2, comma, y2. So in terms of those coordinates, delta y can be written as y2 minus y1, and delta x is x2 minus x1. So in other words, delta y is the vertical separation between the 2 points A and B. Delta x is the horizontal difference between the 2 points A and B. In other words, we call these rise and run. This is delta y is the rise and delta x is the run. So we can further write this as rise over run. So that is another common way of defining the slope of a line. Just find the rise over run and you get the slope. Another one I need to point out, if you can identify this triangle, let me call this point C. So then ABC triangle is a right angle triangle. And let me define this angle in a different color. So let me call this angle theta. Okay. And then you should be able to identify what delta y and delta x are. So delta y with respect to this angle for this right angle triangle, delta y is the opposite side and delta x is the adjacent side. So in other words, I can write down from our trigonometric identities delta y over delta x is equal to tangent of that angle theta. So we have 3 methods to define the slope. This is the first way of defining the slope. This is the second way of defining the slope, rise over run. And then this is the third way of defining the slope. Simply look at the angle the line makes with the positive x-axis and then take the tangent of that angle. So these are the three more common ways of defining the slope or the gradient of a line. If you look at this equation y equals mx, you can notice that if we solve for m, we get m equals y over x. Or if we look for a change in the variables, then we can write it as delta y over delta x. So in that sense, this m is what we call the slope. So slope is basically m in a linear equation like y equals mx. M stands for the slope. The first definition, it says it's the rate of change of y with respect to x variable. Another way of defining is delta y over delta x, where delta y stands for the rise and delta x stands for the run. And the third way of defining m or the slope is simply consider the angle the line makes with the positive x direction and take the tangent of that angle. Let's consider three linear equations. I will take y equals x, then y equals 2x, and y equals 4x. So if I plot these three lines on this xy coordinate system, I'll have y equals x like that, and then y equals 2x like that, and then y equals 4x like that. So you can see when this number over here, when that is increasing, over here it's just 1. That's why I haven't written that down. But when that number increases, the steepness of the line increases. So slope qualitatively is related to the steepness of the line. And that is also very important. So for example, over here 4 is the slope, because I told you this is in the form of y equals mx, and we call m the slope. So this is 4. So it has the highest steepness, the most steeper line. Then y equals 2x, it has a steepness like this, and y equals x has a steepness like this. So that means the angle increases. Steepness increases means the angle the line makes with the positive x-axis, that increases. So that's another way of identifying the slope. Simply look at the steepness of the line. Okay, let's do this example. Find the gradient or the slope of the line given, and also find the angle it makes with the positive x-axis. So as we know, m gives you the slope, and that is defined as the change in y divided by change in x, or I can further write it like y2 minus y1 divided by x2 minus x1. So I'll consider this coordinate as my x2, y2. So x2, and this would be y2, and this is my x1, and this is my y1. So I'm going to substitute, and then you'll see it's like 4 minus 2 divided by 6 minus 1. So I get 2 over 5, or in other words, that means 0.4. So the gradient or the slope of this line is positive 0.4. So that's part 1. The next one, find the angle it makes with the positive x-axis. So that means, if you construct a right angle triangle, it's this angle. Let me call that theta. So we all also know that m, or the slope, is defined as tangent, trigonometric function, tangent of this angle, tangent theta. So if I want to find theta, I can take the inverse tangent and I'll get theta. So that means if I take the inverse of this, I can solve for theta. So that means inverse tangent of m. Okay, and then I have inverse tangent. What is m? We figure that out, 0.4. And then you'll see theta is equal to approximately 21.8 degrees from the positive x-axis. So you can see this angle is less than 90 degrees. So that's how you solve this problem. Now, another important thing, this m is 0.4. That means for any point, any point along this line, the slope is constant. So that means I'll use a different color. For example, let's consider a point over here, and then you draw a tangent to that point, like this. And that makes the same angle, theta, with the horizontal compared to this point. You draw a tangent and you look at the angle theta. It's the same theta. You draw a tangent here and you can see it's the same theta. If it's a linear or a straight line, then m, or the slope, is constant throughout that line. Let's look at some variations of the equation y equals mx, where m, or what we call the slope, is a positive value. So the first one, I'm going to draw y equals mx. We already know the form of this graph. It's a straight line that passes through the origin like that. And then it's going to make an angle with the positive x-axis. Let's call that angle theta. So m is equal to tangent theta. So the next one, I'm going to draw a variation of y equals mx, is y equals mx plus c, where c stands for the y-intercept. So that equation, that line, is something like that. It makes the same theta with the horizontal because you have the same m. So the steepness or the slope is the same. But now it does not go through the origin, but it goes through a point on the y-axis, which we call the y-intercept. So the coordinates of this point is 0, c, where c is the y-intercept. The other variation is y equals mx minus c, where c again is the y-intercept, but in this case, the line is like this. So it makes the same slope, that means the same angle with the horizontal, but this time it's going to intersect not above the x-axis but below the x-axis. So the coordinate of that point would be 0, minus c, where the y-intercept is minus c. So these are some variations of y equals mx equation when m is positive. Now let's look at y equals mx when m is a negative value. How will these lines look like on a xy coordinate system? So for example, let's consider y equals minus 2x, this linear equation. So if we plot this linear equation on this xy coordinate system, it's going to look like this. So that's your y equals minus 2x line. The important thing here is the angle the line makes with the positive x-axis. So this is theta. Here, theta is going to be larger than 90 degrees, but it will be less than 180 degrees. So that means the angle is always in the second quadrant. In this case, if we take tangent theta when theta is in the second quadrant, you'll see that the tangent theta value is always less than 0, or it's a negative value. So that's why you have this negative sign. If there's a negative sign in front of the coefficient, then the slope looks like this. Now another variation of this is with the y-intercept. So let's say that y equals minus 2x plus 1. So this line will intersect the y-axis at 0, 1. So it's going to look like this. And then this y-intercept would be 0, 1. So the general form for this is like y equals mx plus c. But remember, m is less than 0. This is y equals mx, but m is less than 0. In the previous case, we talked about when m is positive. The third variation is y equals minus 2x minus 1. So that means the line would go like this. And then this coordinate would be the y-intercept. This time it's going to be below the x-axis. 0, minus 1. And the general form would be y equals mx minus c with m less than 0. So these are the main types of linear graphs that I want to discuss that will be relevant for our course. Now let's look at some non-linear graphs that are going to be important for our course. So the first one, again, I'll define these the axes. This is y, and this is going to be x-axis, and that's our origin. Now, what is a nonlinear graph or a nonlinear relation or a nonlinear equation? So you would still have your independent and dependent variables like this, and then they are related to one another, but this time the exponents are not 1. For example, the exponent here could be 1, but the exponent on x could be like 2. This is an example for a non-linear relationship. So then I can use this proportionality constant. Again, let's call that proportionality constant m, and then I'll have y equals mx squared. So how would we plot this graph? So it's going to look like this. It will be definitely a curve, not a straight line. It's going to look like this. So y equals mx squared. Now, what is the slope of this curve? So the slope for this curve is position dependent. So for example, if I consider 2 points A and B, how do we find the slope? We draw a tangent to that to the line at that point. So let me use a different color for that. So if I draw the tangent for A, it's going to look like this, and then I can figure out the angle it makes. Let me call it theta, and here again I'm going to draw a tangent to point B, and then I'll define the angle with the positive x-axis. Let me call that theta prime. Obviously you can see theta and theta prime are different, so the slope changes along this line. It's not constant like in the linear case. Here actually we can show that the slope is equal to 2x instead of just a constant. So it's not a constant value. So that is something very important with the nonlinear graphs or equations. The slope depends on the position. In a linear equation, the slope is constant. Okay, but we are not going into these details, but keep that in mind. If you're asked to draw a sketch y equals mx squared curve, then it's gonna look like this. The next one, again I'll define my y and x coordinates. Again, a nonlinear relationship. Let's say this time it's going to be y equals mx, but x is 1/2. The exponent is 1/2. So if you plot this one, it's gonna look like this. So that's your y equals mx 1/2 graph. Again, you'll see the slope is different from point to point. You can select 2 points, then draw the tangent at those 2 points, measure the angle between that tangent line and the positive x-axis. You will see the angles are different. So the steepness, the slope changes from point to point. The next example is y equals 1 over x. So if we plot this curve, the nonlinear equation, it's going to look like this. So that's your y equals 1 over x graph. Similar to that, there's another very important nonlinear equation. That's y equals 1 over x squared. So this is called the inverse square law. Because you can see 1 over means inverse. If you see x squared, that's what it meant by square. So this variation is called the inverse square law, and you'll come across different models that explains this inverse square law. So if we plot 1 over x squared on this same plot, it's going to look like this. It's much more steeper than 1 over x. So it's like this. So this is 1 over y equals 1 over x squared, and this intersection point is coordinate 1, 1. So you can see compared to 1 over x squared becomes 0 very quickly. So this 1 over x will take some time to become 0, but 1 over x squared is much more steeper, and it will reach 0 very quickly, or it's decreasing much more quicker than 1 over x function. The next nonlinear equation that I like to discuss is y equals minus 1 over x. This graph is between the positive x-axis and the negative y-axis, and it's going to look like this. So you'll see that as it reaches, as the x value increases, it will have a horizontal asymptote, and as the y value increases in the negative direction, it will have a vertical asymptote. So this is another important nonlinear graph for our course. The fifth example that I'd like to discuss is the exponential function y equals e to the power minus x, which we defined for x equal or greater than 0 region. Then the function or the nonlinear graph would look like this. And this intersection point, the y intercept it will be 0, 1. The sixth and the final nonlinear equation that I'd like to discuss is y equals 1 minus e to the power minus x. So if we plot this curve, it's going to look like this. As x increases, the y value will reach 1. So that means we have a horizontal asymptote at y equals 1. So this line is the y equals 1 line. Okay, so this is the final nonlinear graph that I'd like to discuss, that I feel like will be important for our course. Okay, now let's talk about some basic differentiation. So here I have a xy coordinate system. So this is my x-axis and this is my y-axis, and that's the origin. And let's say that I have a relation between x and y, which we usually call a function, and this is that function. Let's say that I'm going to consider this point as x comma y, and then a point to the right of that initial point, I'm going to define its coordinate as x plus delta x and y plus delta y. So in differentiation, what we do is that we look at the change in the y variable with respect to the x variable, or as you know, y variable is called the dependent variable, the x variable is called the independent variable. So we look at how the dependent variable changes with respect to the independent variable. So in that sense, I'm going to look at the change in the y coordinate for both these points, and that you can see is delta y. Then I look at the change in the x coordinate, and that's delta x. So if I look at the rate of change in y with respect to x, then that is, so I'll write change in y with respect to x is what we call delta y over delta x. However, previously we discussed this same thing as the slope of that function between the 2 points. So if I define this as theta, that angle, then I can write tangent theta, which is the slope between those 2 points, is equal to delta y over delta x. Now in differentiation, what we do is that we look at this change at a limiting value when delta x goes to 0. So if we look at delta x, the limiting value when delta x goes to 0, the limiting value of delta y over delta x, by definition, this is what we call as the differentiation of y with respect to x. Sometimes it's called the derivative. Derivative of y with respect to x, and also symbolically it's called dy over dx. So that's a very basic idea about differentiation of a function. So dy over dx is the limiting value of delta y over delta x as delta x approaches 0. So that's the definition of the derivative of y with respect to x. Let's look at the graphical interpretation of dy over dx. So this is how we define dy over dx as the limiting value of delta y over delta x as delta x goes to 0. So this is important. What is meant by delta x goes to 0? So what is delta x? If you look at this graph, so this is the same graph that I showed you in the previous slide. Let me label these points as P and Q. Delta x is the horizontal separation between P and Q. So that is this distance. We call this distance as delta x. That's delta x. That's the meaning of delta x. So when delta x approaches 0, that means, in other words, this Q point approaches P point. So as delta x goes to 0, point Q approaches point P. So then what will happen to the slope of PQ? So we can look at that. For example, let's say Q is over here. Then you can see now the new slope is different. The Q point is now over here. You can see the slope changes accordingly. If Q is over here, then you'll have a new slope. Similarly, when point Q is on top of point P, the slope, that is the gradient line, will become a tangent drawn to point P. Like that. And that is the graphical interpretation of dy by dx. So dy over dx, graphically that means the tangent at point P. So when you're given a function to differentiate, we have to use differentiation rules. So I have listed some of these differentiation rules here. So we'll go through one by one, and at the end, let's go through some examples. So the first one is constant rule. So that means C is a constant. So if you take the derivative of a constant, it's 0, because as I told you, the definition of the derivative is you are looking for a change with respect to some other variable. when you have a constant, it does not change. So that's why if you take the derivative of this constant with respect to x, it is 0, because you can see there's no variation with respect to x. For example, let's say y equals 24. If you take dy over dx, you can identify that 24 is just a constant. There's no x dependency here. As a result, this is 0. Similarly, this is called the power rule. So in the power rule, let's say you have a function like y equals x to the power 4. So when you take the derivative of this function, dy over dx, that result is given as you get the exponent. You identify what is the exponent, that is 4. So 4 multiplied by x, 4 minus 1, always 1 less than the original exponent. So then you have 4x cubed, or x to the power 3. So that's what we call the power rule. Then constant multiple rule. In other words, an example would be, let's say, 4 x to the power 4, right? So in this case, we isolate the 4 and we take the derivative of this function x to the power 4. We already did that in the previous example. What is the derivative of this? So that is 4x cubed. So then the answer is 16x cubed. That's the answer when we differentiate this function. You have to identify that it's a variable that is multiplied by a constant. Okay, and then you have the sum and the difference rule. For example, let's say 5x minus 2x squared. So then there's a subtraction. So you simply differentiate the first term, you differentiate the second term, and then subtract the two results. So for example, dy over dx, the first one is simply 5, because you can use the power rule to get the answer. That's how I got it, 5 minus 2, that is a constant, and then the derivative of x squared. Again, for that you can use the power rule, and you'll see that the answer is 2 times x. Then you take the difference between the two, 5 minus 4x. You can do the same thing when you have like a plus sign. Instead of the minus sign, you have a plus sign. Now let's look at the product rule. As an example, let's take the function y equals x times x minus 1. So we have two terms in this function. So when you take the derivative of y with respect to x, what we do is that we take the derivative of the function term by term, that is one term at a time. So I first keep the first term as is and take the derivative of the second term like that, and plus I keep the second term as is and then take the derivative of the first term. That's how you apply the product rule. So then you'll see x, the derivative of x minus x, x minus 1 is simply 1, plus x minus 1 times the derivative of x is simply, again, just 1. So the answer here would be x plus x minus 1, or I can write it as 2x minus 1. So that's an example for the product rule. Now the quotient rule, for example, let's look at a function like this. X minus 1 over x. Then we have to apply the chain rule. So this is the chain rule. So that means if you have a function like e to the power u, if you take the derivative with respect to x, you write e to the power u and take the derivative of u with respect to x, where u is a function of x. So similarly, you can see 2x is a function of x. So if I call that u, I can take the derivative of this function dy over dx. I simply write e to the power 2x and take the derivative of u with respect to x, which is nothing but 2x. And then I get e to the power 2x times 2. Or we can write it as 2 times e to the power 2x. So that's how you do exponential functions, derivatives of exponential functions. The simplest one is this one, but here you are applying the chain rule. Now let's look at differentiating logarithmic functions. So for example, if we have a logarithmic function like y equals 5 raised to the power x, where the base is 5, then dy over dx, according to this rule, is 5 raised to the power x times the natural log of 5. Now here you are applying the chain rule. For example, we can take the a variant of the same function. Let's say y equals 5 raised to the power 3x. So now you can see 3x is our u, which is a function of x. So dy by dx in this case, you write the same 5 base raised to the power 3x, and then the natural log of the base, which is 5, and then you take the derivative of the exponent, which is 3x, and so I'll write it as 3 times 3x d over dx, and then the final answer would be, you will get a 3 from here, 3 multiplied by ln 5 times 5 raised to the power 3x. So that's how you do that one. So then this is 2 other rules for the logarithmic functions. So if you have ln x, you simply take 1 over x. How about taking the derivative of y equals ln 2x? Now it's not x but 2x. Again you apply the same idea, dy over dx. Instead of 1 over x, now we write 1 over 2x, but remember we have to take the derivative of that function, which is 2x, with respect to x. D over dx 2x is 2, so the final answer is 1 over 2x multiplied by 2. The 2 in the numerator and the denominator cancels out, and you still get 1 over x if the function is y equals ln 2x. So this is an application of the chain rule. Now for this one, let's say you have a function like log base 10. So think about a function like this, log base 10. Instead of x, let's put it like x squared. So how would you find the derivative of this function with respect to x? Again, you apply the same idea, 1 over ln of the base, which is 10, multiplied by this term over here, but you can see that term in my example is not x, it's x squared. So I'm going to write x squared, and then I need to do the chain rule. I need to take the derivative of this function with respect to x, x squared. And then your final answer would look like this: dy over dx 1 over ln 10 multiplied by x squared, and then this term will yield 2x. And then you can simplify it further. So if you simplify that, you can see one of the x terms in the denominator cancels out. So now you end up with a 2 in the numerator, and in the denominator you have ln 10 times x. So that's how you do this example that is related to a logarithmic function. Now finally we have the trigonometric function. So if you have sine x, if you differentiate with respect to x, you get cosine x. If you have cosine x and you differentiate with respect to x, you get minus sine x. So keep in mind the minus sign. That is very important. That's a point where people miss that minus sign. And then tangent x, dy over dx tangent x is secant squared x, or sometimes it can be written as 1 over cosine squared x. Now as an example, let's try to do y equals cosine 2x plus 1. So how are we going to take the derivative of this function with respect to x? So the first thing you have to identify that instead of cosine x, now you have cosine 2x plus 1. So this is like a function within a function. As a result, I am going to call this 2x plus 1 as u, and then the entire function becomes cosine u. So I'll take the derivative of cosine u with respect to u like this, and then I'll take the derivative of u with respect to x. So here what I have done is that I have applied the chain rule. So then I'm going to differentiate cosine u with respect to u. So that is minus sine u times du over dx, which is d over dx 2x plus 1. Now I can substitute for u. That would be minus sine 2x plus 1, and the derivative of 2x plus 1 with respect to x, that's going to be simply a 2. So then my answer is minus 2 sine 2x plus 1. Okay, now let's do some example problems using those rules that we discussed. So this is the first function. Let's find the derivative with respect to x. So dy over dx. And then you can see there's a constant and x squared plus a constant times x minus a constant. So I'm going to do it like this. I'm going to pull out the constant and then take the derivative of x squared. Again, for the second term, I'm going to pull out the constant and then take the derivative of x with respect to x. And the third term is simply a constant. So I'm going to write it like this, and I know if it's a constant, its derivative is 0. So here, the derivative of x squared is 2x. So I have minus 3 times 2x plus 2 times 1 minus 0. And then the final answer, dy over dx, is minus 6x plus 2. So that's the answer for the first example. In the second example, we can see it's a function within a function. So first, I'm going to differentiate the outer function and then the inner function. You can see the outer function is 2 times 2x cubed plus 5x minus 11, And now I'm going to differentiate the inner function, which is d over dx, 2x cubed plus 5x minus 11. Now I'll distribute this differentiation for each term. I have 2 times 2x cubed plus 5x minus 11, and then I'll have the differentiation of 2x cubed is 2 times 3x squared, and then this is just 5 because you are differentiating 5x, then you have just the coefficient 5, and then this is a constant, so differentiation of a constant is 0. Okay, and then you can write this as 2 times 6x squared plus 5 multiplied by 2x cubed plus 5x minus 11. So that's the solution for the second example. In this third example, again, we have to take dy over dx. So dy over dx, and I'll just separate out the constant and then take the derivative of the function, which has a negative exponent. So then I have 5 and the exponent is minus 2 over 3, and then I can write x minus 2 over 3 minus 1. So simplifying this entire thing, I can write it as minus. In the numerator I have a 10, in the denominator I'll have 3, and if you like you can take this negative exponent to the denominator and the exponent will change the sign. So x plus 5 over 3. So that's the answer for the third example. Now the fourth one, dy over dx. Again, there are two terms, so you can distribute the derivative like this. And then for the other term, like this. And then in the first term, you have a positive exponent. In the second term, you have a negative exponent. So you can write this as 3 1/2, and here it would be x plus 1/2 minus 1. And for the second term, I can take out this negative exponent like that, and then here I have x minus 1/2 minus 1, and then you can simplify this further. 3 over 2 x raised to the power minus 1/2, then minus times minus, it becomes plus for the second term, 1/2 x minus 3 over 2. Now if you like, just like in the third example, you can take this term to the denominator, so then the negative exponent becomes positive exponent. But I mean, if you keep it like this, it's still going to be correct. There's nothing wrong with this way of expressing the final answer. So for this fifth example, I'm going to use the product rule. I'm going to first take the derivative of this term and then keep the other two as is. Then I'm going to take the derivative of the second term and keep the terms 1 and 3 as is. And finally, I'm going to take the derivative of the third term and keep 1 and 2 terms as is. So dy over dx, I'm directly going to take the derivative of the first term. You can see it's just 1. And then I'm going to write the other two terms as is. Plus, Now I'll take the derivative of the second term. So I'll write the first term as is, and then the second term I'm going to take the derivative, which is again just 1. And then I'll write the third term as is, and finally the third term. So first two terms I'll write them as is, and then take the derivative of the second term. Third term, you can see it's an x squared, so it will be 2x. So that's how you do the differentiation for a term like this. So then you can simplify it any way you like it. So x minus 2, x squared plus 1, and then I have x plus 4, x squared plus 1, and then I have plus 2x times x minus 2, x plus 4. So you can further simplify this. I'll do one more step so I can see x squared plus 1 as a common term. So x squared plus 1. And then I'm going to add these two terms because they are common to x squared plus 1. So I'll have 2x, and then I'll have a plus 2. And from this term, the third one, I'll get 2x, x minus 2 times x plus 4. So again, you can simplify this further, but I'm going to keep it like this. The idea is to show you how to do the derivative, not simplifying and getting the final answer. It's basically how to take the derivative of a given function. Now the sixth one, we have to apply the quotient rule for this one. So dy over dx, what I'm going to do is that I'm going to square the denominator. So I'll write this as x 1/2, because square root of x is x to the power 1/2, x 1/2 plus 1 squared, and then I'm going to write this denominator in the numerator like this, x plus x 1/2 plus 1, and then I'll take the derivative of this term, the original numerator, and you can see x to the power 1/2. So I'll have, when I take the derivative of that term, I'll have 1/2 x to the power minus 1/2. Then minus, and then I'm going to keep the numerator as is, x to the power 1/2 minus 1, and then take the derivative of the denominator. So that would be 1/2 x to the power minus 1/2. So what I have simply done is I have taken the derivative of this term, x to the power 1/2. So you can see when you take the derivative of that, you'll get 1/2 x to the power 1/2 minus 1. And when you solve that, you'll get the minus 1/2. So that's the same thing you see over here as well as for this term. So I'm not going to simplify this any further, but you get the idea. Like when you take the derivative of a quotient, this is the process that you have to follow. Further simplification is possible, but I'm not going to do that over here. Now we can jump into example number 7. Here you have a natural logarithmic function. So, and there are two terms. So I'm going to do the derivative for each term, dy over dx. The differentiation of ln x is 1 over x. So I'm going to simply write that 1 over x. And the differential or the derivative of x cubed is 3x squared. So this solution is rather straightforward. Now for example number 8, you can see it's a product of two functions, x squared and e to the power x. So again, I'll take the derivative with respect to x, and first I'll take the derivative of the first term. So d over dx x squared, and I'll keep the second term as is, and then I'll take the derivative of the second term like that. So here I'll have 2x e to the power x plus x squared, and the derivative of e to the power x is simply e to the power x. So that's the solution, the answer for example number 8. Okay, now let's do some examples involving trigonometric functions. So example 9, I can see a product, so I have to apply the product rule. So dy over dx, I'm going to take the derivative of the first term, so that's sine x. When you take the derivative of sine x, that's going to be cosine x. And I'm going to keep the second term as is. Instead of writing the square root x, I'll write it as x to the power 1/2 plus I'll keep the first term as is, sine x, and then take the derivative of x to the power 1/2, which would be 1/2 x to the power minus 1/2. Now again, you can further simplify this, but I'll keep it as is because objective is to give you ideas on how to do the differentiation part. The 10th one, again there's a product, so dy over dx, I'll take the derivative of the first term, so sine squared x. When I take the derivative with respect to x, it becomes 2 sine x, and then the derivative of sine x, which would be cosine x. So this entire term gives you the derivative of the first term. Now I'll write down the second term as is without taking its derivative, plus the first term sine squared x, and now I have to take the derivative of the second term. So the derivative of cosine x would be minus sine x. Now let's look at example 11. As you can see, this is a function within a function. The outer function is the sine function and the inner function is the cosine function or the cosine x. So dy over dx, first I'm going to take the derivative of the outer function, that is cosine x, and then I'll take the derivative of the inner function, which is going to be minus sine x. And then I can rewrite this as minus sine x times cosine x. So that's the answer for example 11. Example 12, you can see it's an exponential function, but this time the variable is not x but t. The exponent is a product of this t variable. So instead of our usual dy over dx, I'm going to write dy over dt, because as I told you, the independent variable is t, not x. So exponential functions, when you take the derivative, you first write the same function. So exponential t times cosine 3t, and then you take the derivative of the exponent with respect to t. T times cosine 3t. And you can see it's a product, so then you apply the product rule in the next line. So it's going to be dy over dt. You have e to the power t times cosine 3t, and then you take the derivative. So the first term t, so it's just 1, and then I'll keep the second term as is, plus I'll keep the first term and take the derivative of the second term. So cosine 3t, it would be minus sine 3t, but then again you can see 3t has to be taken, we need to take the derivative of 3t, that's going to be 3. So that's your answer, and then you can go ahead and do further simplification, but I'll pretty much stop at this third line, cosine 3t, and then I have cosine 3t minus 3t sine 3t. So that's the answer for example 12. Example 13 involves a logarithmic function with base 6 and the exponent minus 1 over x. So when we find dy over dx, we first write the same exact function, 6 to the power minus 1 over x, and then multiply that by the natural log of the base, which is 6, multiplied by the derivative of the exponent with respect to x, that is d over dx minus 1 over x. So when we simplify this, we have 6 raised to the power 1 over x ln 6, and then d over dx minus 1 over x is simply 1 over x squared. So you can finally write this as dy over dx 6 to the power minus 1 over x ln 6 divided by x squared. So that's the answer for example 13. Example number 14 includes a logarithmic function. Inside the logarithmic function, there's a product x squared multiplied by sine x to the power 4. So here I can use this identity for logarithmic functions. ln a times b can be written as the sum of ln a and ln b, the sum of those two. So as a result, I can simplify this logarithmic function as ln x to the power 2 plus ln sine x to the power 4. Further, the exponents can become simple multipliers. So 2 times ln x plus 4 times ln sine x. Now I can take the derivative of this much simplified version of the function. dy over dx now becomes 2 1 over x, and then the second term 4 1 over sine x, and the derivative of sine x, which is cosine x. So the final answer can be written as 2 over x plus 4 cosine x over sine x. So this is the solution for the 14th example. Example number 15 includes a quotient, and the numerator of the quotient is a logarithmic function. So I'm going to apply the quotient rule here. Dy over dx, I'm going to first square the denominator and write it in the denominator. so x to the power 6, and then take the denominator, the numerator, x to the power 3, and then differentiate the numerator, which is 1 over x. The derivative of ln x is 1 over x. So I'm going to write that down, minus the numerator times the derivative of the denominator, which is 3 times x squared. So now you can further simplify this function, x squared minus 3 times x squared ln x over x to the power 6. We can further simplify this. We can pull out an x squared from the numerator and an x squared from the denominator. So this would be 1 minus 3 ln x over x to the power 4. So that's the answer for example number 15. In example 16, again I have a logarithmic function. This time it's base 10 with a numerator and a denominator. So before differentiating the function, I will simplify this further. For that, I'm going to use log base 10. If it's a over b, then I can write this as a difference between two logarithmic terms. So like log base 10a minus log base 10b. So I'm going to use this to simplify y. So then I'll get log base 10 3x minus log base 10 x plus 1. Now I can differentiate each term, dy over dx, 1 over, I'm going to write this term 3x, and the natural log of the base, which is 10, and then the derivative of 3x. I need to multiply the entire thing by the derivative of 3x with respect to x, which is simply 3. Now I'm going to do the same process for the second term, put the minus sign, and 1 over, I write the term within the parentheses in the denominator x plus 1, and then take the natural log of the base, which is ln 10, and then again multiply by the x derivative of x plus 1, which is simply 1. So that's how you get the answer, and then that's the solution for example number 16. In example 17 and 18, we are going to talk about higher order derivatives. For example, the first order, second order, and the third order derivatives of these functions with respect to x. So first we'll take the first order derivative dy over dx for example 17. Sometimes this is also called y prime. So y prime would be 5 times the derivative of x to the power 4, which is 4x cubed, plus 3 times derivative of x squared, which is 2x, and minus 6 times the derivative of x, which would be just 1. And I have a constant. The derivative of a constant is simply 0. So this can be simplified as 20x cubed plus 6x minus 6. The second derivative is simply taking the derivative of the first derivative. So d squared y over dx squared. Sometimes that's called y double prime. And that would be 20 times the derivative of x cubed, which is 3x squared, plus 6 times the derivative of x, which is 1. And then I have a constant, so the derivative of a constant is 0. And the second derivative of example 17 would be 60x squared plus 6. The third derivative, d cubed y over dx cubed, sometimes it's also called y triple prime, is simply 60 times the derivative of x squared, which is 2x, and then I have a constant So the derivative of a constant is 0. So the answer for this would be 120x. Similarly, if we look at example 18, here we have a trigonometric function. So the first derivative dy over dx or y prime is 2 times the derivative of this cosine term. So that is minus sine 2x times the derivative of 2x, which is simply 2. So we can write this as minus 4 sine 2x. Now for the second derivative, we have to take the derivative of the first derivative, that is d squared y over dx squared. Also it's called y double prime. So then I take minus 4 and take the derivative of sine 2x, which is cosine 2x times 2. So the second derivative of, for example, 18 would be minus 8 cosine 2x. Now for the third derivative, I take the derivative of the second derivative. So d cubed y over dx cubed equals y triple prime. So that is equal to minus 8, and I take the derivative of cosine 2x, which is minus sine 2x times 2. So the answer would be plus 16 sine 2x. In this section, we will talk about how to find the maximum and the minimum value of a function. So let's consider an arbitrary function given by y equals f of x. And if we represent this function graphically on an xy coordinate system, let's say that it's going to behave in this way. And let's call this as point P. Now, if we take dy over dx or df of x over dx at point P, it's going to represent the tangent drawn to the curve y equals f of x at point P. It basically gives you the tangent line. So if this tangent line is horizontal, or in other words, the slope of f of x at P is 0, that means dy over dx at P is 0, we can conclude 3 different situations. The first situation is at P, the function f of x is a maximum. The second situation is at P, the function f of x is a minimum. The third situation is at P, the function f of x represents an inflection point. Okay, so if we look at the first situation, the maximum, so graphically that means at P you have a local maxima. So you look at the slope or the tangent line, and then it's horizontal, stating that dy over dx at P is 0. In this second situation, the minimum, you have a local minimum, and point P, at point P you have the tangent line horizontal, again the slope or dy by dx at P is 0. For the inflection point, you can have two cases. A situation like this, or a situation like this. Here again, if we think that's the place where point P is, you have a horizontal tangent line and dy by dx is 0. Again, somewhere here, you have a horizontal tangent and dy by dx is equal to 0. So in both these cases, dy over dx at P is 0. So you have three cases. When dy by dx equals 0, it could be a maximum, it could be a minimum, or it could be an inflection point like this. But how do you really know whether you have a maximum or a minimum or an inflection point? For that, we have to look at the second derivative of the function, namely d squared y over dx squared. Now, in the case of a maximum, what you'll see is that the slope, initially it's positive, and then the slope becomes 0, and the slope then becomes negative. So slope goes from positive to negative, telling that the second derivative is negative. In the case of a minimum, the slope becomes negative. Initially it's negative, then the slope is 0, and then the slope becomes positive. So you start with a negative slope, through 0 it becomes positive, and as a result the second derivative of the function d squared y over dx squared is positive. In the case of an inflection point, the slope starts with a negative value, then at point P the slope is 0, then again it becomes negative, or the other way. That means the slope initially is positive, then at point P the slope is 0, and then again the slope is positive. So the slope goes from positive to positive or from negative to negative, meaning if you take the second derivative of the function d squared y over dx squared, it's 0. So in order to know exactly if you have a maximum, a minimum, or an inflection point, this first derivative of the function has to be 0, as well as you have to look at the second derivative. If the second derivative is negative, then you have a local maxima. If the second derivative is positive, then you have a local minima. If the second derivative is 0, then you have inflection points, which are physically pretty rare. Now let's apply the concepts we learned earlier to solve some examples. So in this example 1, find all local maxima and minima for this function. So the first thing we are going to do is take the derivative with respect to x, dy over dx. So that would be 2x minus 1. And since we need all the maxima and minima for this function, we are going to equate the derivative to 0, and then you can see x is equal to 1/2. So we are going to get x equals 1/2. Now we don't know whether this is a maxima, a minima, or an inflection point. So the next step is to take the second derivative of this function. So if you take the derivative of this function, then you are going to get 2, and that's greater than 0, saying that this point corresponds to a minimum value. So what we have is only one minima. There are no inflection points or maxima for this function, but there's only one minima at x equals 1/2. There's another way of figuring out whether it's a minima or a maxima. So that's using graphical methods. So I'll call that the alternative method. What we do is that we draw a number line. So this is the x-axis, because our independent variable is x, and I'm going to put x equals 1/2 somewhere over here. And I know at x equals 1/2 the derivative is 0, so that means the slope is 0, or the tangent line is horizontal. Now let's look at a value less than x equals 1/2. For example, let's say x equals 0, and then I'm going to substitute x equals 0 in dy over dx, that is in 2x minus 1. So then you'll see that dy by dx is -1, saying that we have a negative slope. So something like that. And then I'm going to look at an x value larger than 1/2. For example, x equals 1. Again, if I substitute in dy over dx, 2 times 1 minus 1 is plus 1. So greater than 0. So the slope for x equals 1 is greater than 0. So this graphical technique shows you that at x equals 1/2, we have a minimum value. So the curve would look like this, indicating that at x equals 1/2, there's a minimum value. And also, if we like, we can find what is that minimum value. So y minimum, we simply substitute 1/2 for this x position, for this x variable. So we get 1/4 minus 1/2. So the answer y minimum would be minus 1/4. So that's how you identify at what x value you are going to get a maxima or a minima, and then exactly finding the y value of at that minima or maxima. This is how you do that one. Just like the previous example, for this function, let's try to find a local maxima and minima. So first we have to take dy over dx. The first term is a constant, so it's 0. I'm not going to write that. The second term, the derivative is 3. And for the third term, the derivative would be 3x squared. So for the simplification, I can pull out a factor of 3. So then I'm going to get this result. So for minima or maxima, I need dy over dx equals 0. In other words, 1 minus x squared equals 0. So that's going to yield x equals -1 or x equals +1. Now I'm going to look at the second derivative. d squared y over dx squared. You can see if I do that for the first term, it's a constant. However, the second term, I'm going to get 2 times x. The derivative of x squared is 2x. So the final result would be minus 6x. Now I'm going to substitute what happens to the second derivative at x equals minus 1 and x equals plus 1. So if I substitute x equals minus 1 at x equals minus 1, d squared y over dx squared would be minus 3, sorry, it would be minus 6 times minus 1, positive 6 or greater than 0. At x equals plus 1, the second derivative d squared y over dx squared will be minus 6 multiplied by 1, which is minus 6, and that is less than 0. So this shows us that at x equals minus 1, the function f of x equals 2 plus 3x minus x cubed will have a minima. It's going to have a minimum value. And we can even find that minimum. Y minimum, I'm going to simply substitute x equals minus 1 in this equation, the original equation. So 2 plus 3 times minus 1 minus 1 to the power 3. And then this is going to yield 2 minus 3 minus 1. It will give me minus 2. So the function will have a local minima at x equals minus 1. That value would be y equals minus 2. Then at x equals plus 1, the function f of x or y, 2 plus 3x minus x cubed will have a maxima. Like here, it will have a maxima. And we can find that maximum value, y max. Simply substitute x equals 1 in the original cubic function. So 2 plus 3 times 1 minus 1 raised to the power 3. And then you will have 5 minus 1 equals 4. So at x equals 1, y will have a local maxima that is equal to 4. So this is how you do example number 2. Now let's look at the third example. This is a kinematic equation that comes quite regularly in physics. So y's of t, as you can see, it gives the displacement in the y direction at time t, where y direction is usually the vertical direction. v0y is the initial velocity in the y direction, which is a constant. T is time, and that is the variable here, the dependent variable. 1/2 is a constant. G is the acceleration due to gravity, 9.8 meters per second squared. That is also a constant, and t squared is again time squared. So we first take dy over dt, because here the variable is t. The first derivative of the function with respect to time, and then you'll see that's equal to v0y minus 1/2 g and the derivative of 2t, t squared would be 2t. So it's going to yield v0y minus gt. Now, to find maxima or minima, what we do is that we equate dy over dt to 0, and this is going to yield a t value of v0y over g. So we still don't know, even though we got this t value corresponding to dy over dt equals 0, we just don't know whether this actually at this point we are going to get a maxima or a minima. So for that we have to take the second derivative with respect to t, d squared y over dt squared. So if I take the second derivative of this function, you are going to see that it's equal to minus g, which is a negative value. So that means it's guaranteed that we are going to get a maxima at t equals v0y over g. So at t equals v0y over g, the function yt has a maxima. And we can even find that maxima. So y max is equal to v0y. We can substitute this t value, v0y g minus 1/2 g v0y g squared. So from the first term we have v0y squared over g, and in the second term we have v0y squared. There's a 2 here and a g. So then your answer y max is v0y squared over 2g. So at t equals v0y g, the y value attains a maximum that is given by v0y squared over 2g. So you can even plot y versus time, and you'll see something like this. So the x-axis is going to be your time axis, that's the origin, and the y-axis is this y's of t. And if we plot this, it's going to be an inverted parabola like this. And then you'll have this maximum that is equal to v0y squared over 2g, and that maximum value for y's of t is achieved at t equals v0y over g. So this is an example from physics that is related to finding the maxima and minima of a function. In this section we are going to talk about integration. Again, a very important skill that you should know when you study physics. For example, let's look at a function called y equals f of x. Now, we already know if we differentiate this function, we are going to get the derivative of this function. So that means either it can be represented as dy over dx or df of x over dx. So this process of going from the function to its derivative, that's what we call a differentiation. And this is usually represented by d over dx. Now this d over dx is a mathematical operation. Keep that in mind. It's a mathematical operation. It's like adding, subtracting, multiplying, and dividing. It's another mathematical operation. Suppose that we are given the derivative of a function and we want to find the original function. So in that case, we have to do this operation from the derivative, how to obtain the original function. So this process is what we call integration. And sometimes, since it is the reverse operation of differentiation, it's called anti-differentiation. And its symbol is written like this. So that's the symbol of integration. And then you have dx, where x is the variable you are integrating the function with. And over here, you have to place that function, the function that you are integrating with respect to x. Usually, this function is called the integrand. So, for example, you can have something like this: 2x squared plus 1. So that's your integrand, and you are integrating this function with respect to x. So in this respect, one way of looking at integration is as the inverse operation of differentiation. So I'd like to consider this as interpretation 1. Integration is the inverse operation of differentiation. Let's look at this example to further understand the opposite nature of differentiation and integration. So I have three common physical quantities that comes in physics: displacement, xt, that is displacement as a function of time, then velocity, v is of t, acceleration is of t. Now if we are given displacement and if we want to find the velocity as a function of time, what we do is that we take the derivative of displacement as a function of time, that is this quantity. If we want to find the acceleration and we are given velocity, then we differentiate velocity with respect to time, like this: dv is of t over dt. Or else we can take the second derivative of position with respect to time. Now, suppose that we are given acceleration and we want to find the velocity, that is, we are going in the opposite direction. In that case, what we can do is that we can integrate the acceleration function with respect to time, and this will yield the velocity as a function of time. And suppose that we are given velocity and we want to find the displacement, that is in this direction. What we do is that we integrate the velocity function with respect to time, and then we get the displacement. So you can see the inverse or the opposite nature of these two operations, differentiation and integration. we can consider integration as a method of summation, especially when the function that we are integrating is changing. It's not constant and it's always changing. So I consider this as the second interpretation for integration. So as an example, we can think about finding the area. For example, let's look at an xy coordinate system. So this is my x-axis and this is my y-axis. I'm going to consider a constant function. Let's call it y equals 2. So you can see it's just a constant. It's a line horizontal to the x-axis, and over here it's 0, 2 with a y-intercept of 2. And at this point you have the origin, and let me call this x equals 2. I want to find the area between the y equals 2 line and the x-axis with the limit as x equals 2. So that means I want to find this area. You can see it's extremely straightforward. Area is equal to length multiplied by the width. The length is simply 2 and the width, that is the height in this case, is 2. So the area is simply 4 units. Suppose that we have a function that changes with x. So y equals f of x. Let's consider that's our function. And let me define it up to a certain x value. Let's call it x naught. So in this case, now I want to find the area between the x-axis and the curve y equals f of x. So how am I going to do that? So this is where we can apply integration as a summation. So we are going to break up this entire area into vertical slices. So I'm going to show you some slices with equal width. We can call that width delta x. And then we cover the entire area by these vertical slices. So if we consider one such slice, let's call that our ith slice. We can find the area of this individual slice because we know the width. The widths are equal, each one having a width of delta x. And for the ith slice, this height is fxi. So then that area of that slice would be f of xi times delta x. It's simply height times the width. Now if we add all these slices, let's say that there are n number of slices. This entire region is sliced up to n vertical slices. In that case, if I add up all the areas of those tiny slices, so that means I goes from 1 to n, uppercase n, then I would get the total area. Total area. So that means that gives me the total area. Now what I'm going to do is that I'm going to make this width, delta x width of a slice extremely small. So that means at the limit where delta x goes to 0, in other words, when delta x goes to 0, what happens to this n, in other words, that means when n goes to infinity, we can replace this summation by an integration of the function f of x with respect to x. So we simply call it f of x dx. And we call this an indefinite integral. That is when the lower limit and the upper limit are not defined. However, if we look closely, we can see the limits can be defined. So that means x goes from 0 because the variable is x. So x has a lower limit of 0 and an upper limit of x naught. And then f of x dx. If the upper limit and the lower limit are defined for an integral, that's called a definite integral. In physics, most of the time we'll come across this latter one where the upper limit and the lower limit are defined. So you are eventually finding a definite integral. When we use integration as a method of summation, one of the most important things is defining this elemental unit. In this case, the vertical slice. It could be finding the total area, the total volume, total mass, or any other physical quantity. As I told you, one of the most important thing is defining this elemental unit. Now let's look at two examples where we first define the elemental unit and then use integration to sum up all those elemental units to find a certain physical quantity. So in this example, we have to find the total mass of a one-dimensional rod of length L if its mass per unit length is given as a function of x. So since this is a one-dimensional rod, it does not have any thickness, the mass per unit length is what we call the linear density. And as you can see, it's not a constant, it changes with the position of x, it changes with x. So usually density is defined as mass per unit volume or mass divided by volume. This is for the three-dimensional case. Sometimes instead of the three-dimensional case, we might have two-dimensional or one-dimensional. So in the two-dimensional case, we define an area density. And that is mass per unit area. This is two-dimensional. And in this particular example, we have a linear density. So that means mass divided by a length. So in this respect, the first density, or like the conventional density, can be called a volume density. So let's look at this question. So what we need to do first is to find this element, the linear element that pretty much will help us to sum up the entire length of the rod. So this is what I'm going to do. I'm going to consider a tiny piece of this rod along the x-axis. So you can see I'm going to take this part as my elemental unit. So let's consider that particular element to be a distance x from the origin, and let me call its width or the thickness, let me call it dx. So as a result, what I can do is that I can find the mass of the length element dx would be, simply I can use this idea, mass is equal to linear density multiplied by the length. So linear density is lambda x times the length. The length as I defined is dx. So you can see that's the mass of this tiny length element. Now I'm going to, as I told you, I'm going to divide the entire length from 0 to L into tiny length elements like this. The entire length is divided. So what I'm doing is that in order to find the total mass of the rod is simply the summation of all those length elements. So instead of writing a summation, as you know, we replace that summation by an integral. In this case, it's going to be a definite integral because the lower limit and the upper limit are defined. So lower limit 0, the upper limit is L, and then we have that element lambda x times dx. So now we can write lambda x explicitly, 0 to L e to the power minus x times dx. In the second example, we have to find the total electric charge that is deposited on this washer. The washer has an inner radius of, you can see, an inner radius of R1 and an outer radius of R2, and there's a charge density, area charge density on this washer, and we need to find the total charge that is deposited on this washer. So the area charge density is given as sigma R. So that means it changes with the radial direction. So the first thing, we need to find the area element. So I'm going to consider the area element at a distance r from the center. Now you can see from the symmetry of this shape, I'm going to consider the area element as a concentric circle that is concentric to this washer. So it's going to be something like this. And since I'm looking at an area, it should have some sort of a thickness. So this is, even though I'm drawing it like this, it has to be circular. But you get the idea. So that's the area element. And it has a thickness. The thickness here is dr. So area element is the circumference times the thickness for this element. So circumference is 2 pi r, that is for a circle with radius r, and then the thickness dr. So this will give me the area element. However, we are not trying to find the total area. We are trying to find the total electric charge that is deposited on this washer. So then to get the charge element, so electric charge element, we need to multiply the area element by the area charge density. So if area charge element is called dq, the area element, if I call it dA, and then area charge density as given sigma r, then this is what I need to find out. So I already know dA, which is 2 pi r dr, and then I need to multiply by sigma r, which is the area charge density at a distance r from the center of this washer. Now, in order to find the total electric charge, I simply sum up all these electric charge elements. So let me call the total charge deposited on the washer as Q. That is the summation of all these dq elements. And however, dq can be written in terms of this r variable. So I have 2 pi r sigma r dr. So you can see the charge is transformed into a radial distance. So total charge. So as a result, because we are measuring the radial distance, now we can apply the lower limit and the upper limit. So the lower limit in terms of r, you can see the washer starts with an inner radii of r1 and ends at an outer radii of r2. So the lower limit is going to be r1 and the upper limit is going to be r2. So I have 2 pi r. Sigma r is explicitly 2r squared plus 1 dr. And you can see 2 pi is common and I can take it is a constant. So I can take it out from the integrand and then I have 2 pi r1 r2, and I'm going to distribute this dr. I will have 2r cubed plus r, and I need to take dr of this. So this part, the integrand, we need to use rules of integration to solve this one. Okay, let's look at some rules of integration. We'll first look at integrating a constant with respect to x. So this is the constant k. You can see the answer is k times the variable, that is in this case x, plus a constant which we call constant of integration. So as an example, let's look at integrating 5 with respect to x. Then you will get 5 times x plus c. Now always you can check if your answer is correct. So that means you have to take, when you get this answer, you can take the derivative of this answer and see whether it's the same as the integrand. So this one is what we call the integrand. If you remember that, this is integrand. And the derivative of your answer, that is, you take d over dx 5x plus c, that should equal the integrand. Because as I told you at the beginning, integration is the reverse operation of differentiation. So when you get your answer, you should be able to differentiate that answer and then get the original function that you integrated, or the integrand. So in this case, this is right, 5x plus a c. When you take the derivative, you get 5. Now the reason we are adding this constant c, as I told you, is to represent all the functions with the same derivative 5. For example, you can think about 5x minus 9 function, 5x plus 100, 5x minus 0.99, or 5x plus 2. Now all these functions will have the same derivative. If you take d over dx, you'll see you are going to end up with 5. So that's why you put a c to represent all the functions with the same derivative. Now the next rule is integrating x to the power n with respect to x, where n can be any number, however it cannot be equal to minus 1. For example, again, let's check out an example, integrating x to the power, let's say 7 with respect to x. So you have to identify that this exponent is what we call this lowercase n. That is your lowercase n. So then your answer would be x to the power 7 plus 1 divided by that new exponent plus a c, or you can simplify that, x to the power 8 divided by 8 plus c. So always in this case, when you integrate, you raise the exponent by 1 and divide that value by the new exponent. So if it was x to the power 9 integrate with respect to x, you get x to the power 10 divided by 10. Again, what you can do is you can check whether your answer is correct. That is, if you differentiate this function, that is x to the power 8 divided by 8 plus c, if you differentiate this, you should get the original function that you integrated, or the integrand, and you'll see that it's going to be x to the power 7. So this shows you that your answer is correct. This is a very good way of knowing whether you did your integration correctly. Just use that solution, take the derivative of that, and see whether you get the original function or the integrand. Let's look at integrating 1 over x with respect to x. You can see the answer is natural log of x plus a c. So if you recall, we call this an indefinite integral. Now suppose we have this integration, let's say 1 over 2x dx. How are we going to do this integration? It's not 1 over x, but it's 1 over 2x. So you identify that there's a constant 1 over 2, and you can take it out from this integral. That is a constant times 1 over x dx. You can keep it like that. And then you can apply the previous rule for this integration. Integrate 1 over x dx, so that would be ln x. So you keep 1/2 times ln x, and since this is an indefinite integral, you simply add the constant of integration, and that's your answer. And always you can check if you got your answer correct. Simply differentiate this function. So you can always check this. 1 over half ln x plus c. If you differentiate this, you'll get 1 half times the differentiation of ln x is 1 over x, and the differentiation of the constant is 0, and you get the original function that you integrated, or what we call the integrand. So that's how you do this example. Another very important rule is you have two functions, either it's a sum or a difference. Then what you do is that you can distribute this integral to all these functions. And if there are constants like k1 and k2, as I did in the previous example, you can pull them out from the integral to the outside. Okay, so let's try to do an example. This time I'll do a definite integral just for a change. So let's say that we have a lower bound or a lower limit of r1, where r1 is a constant. The upper limit is r2, and then this is my function 2r cubed plus r, and I'm integrating it with respect to r. So you need to put this dr. So how are we going to solve this? So I'll apply the above rule. I can identify the constants. So in the first term, there's a 2, integration from r1, r2, and then the function is r cubed dr, plus, there's no difference here, it's just a summation, so plus, then the constant, which is just 1, so I'm not going to put 1, r1 to r2, same upper limit and the lower limit, and here I have r dr. So now I have distributed the integration throughout all terms. Now I just need to take the integration. So 2, you can see this is r cubed. So I'm going to apply that exponent rule. So I'll have r to the power 4 divided by 4. But now I need to apply the lower limit and the upper limit. So this is how you do that. Usually we put square brackets and we put r2 here, the upper limit, and over here the lower limit. And then I'm going to the second term. There's a constant 1, so again I'm not going to put that 1. When you integrate this, you'll get r squared divided by 2, because before integration you had r. After integrating, you'll need to add an exponent to this function. So r squared over 2 and divide by the new exponent. Again, applying the limits like that. And here, since we are doing a definite integration, we are evaluating a definite integral, there's no need to put a constant of integration. So then the final answer would be, you simply apply the limits. So you have r2 to the power 4 divided by 4 minus r1 to the power 4 divided by 4. That's the first term. And the second term, r2 to the power 2 divided by 2 minus r1 to the power 2 divided by 2. So whenever you apply the lower limit and the upper limit, you can see you are going to take a difference in that case. So this is your final answer for this example. The next rule of integration is integrating an exponential function. So if it's e to the power x dx, then you simply have the same function e to the power x plus c, the constant of integration. However, let's look at an example like this. Now we have e to the power 2x dx. So in this case, you again write that same function e to the power 2x, but you have to divide it by 2. Then add the constant of integration. Now, you can always check if you got it right by simply differentiating your solution, your answer. So e to the power 2x over 2 plus c. So if you differentiate this, you'll see that you're going to get 1/2, and then here you'll have 2 times e to the power 2x plus 0. 0 is for the constant of integration. And then you'll see you're going to get e to the power 2x. So that means you get the original function that you integrated. So this solution is correct. Another example that we can try out is, let's say, integrate exponential function e to the power minus x dx. So if we if we integrate this, you need to put a minus sign in front of the original function e to the power x minus x plus c. Again, you can see, differentiate this entire function and you will see that you end up with e to the power minus x. So that's your answer for that one. In this rule, we have a base a and an exponent x. So when you have a function like this, a to the power x dx, this is how you would integrate it. So again, I'll do an example. Let's say that you have a base 5x dx. Then your answer is simply, in the numerator you put the same original function, but you have to divide it by the natural log of the base and put the constant of integration. We can try out another example related to this rule of integration. So integrate, again we can try out base 5, but this time the exponent, let's say minus 3x dx. So how are we going to do this one? So I'm going to make a substitution. Let's say that u is a variable that I'm going to define, and u is minus 3x. So I'm going to take that and I'll differentiate this relationship. So you'll have du equals minus 3 dx. So wherever I find dx, that means I can substitute minus 1/3 du. So I'm going to transform this original integral from x to u. So 5 minus 3x becomes u, and dx can be replaced by minus 1/3 du. The minus 1/3 I can pull it out from the integral. So minus 1/3 goes over there, and then I have 5u du. Now this is simply this integral. Instead of x, I have u. So then I can apply the rule, minus 1/3. In the numerator, I have 5u, and in the denominator, I have the natural log of the base, which is 5, plus c. But as you know, u is a user-defined variable. So now I need to replace that with minus 3x. So my final answer is minus 1/3. In the numerator, I'll have 5 minus 3x, where I have replaced u by minus 3x, and then divide the entire thing by the natural log of the base, which is ln 5, and c. So that's the answer to this example. Now let's look at integrating trigonometric functions, the main functions cosine x and sine x. So if you have cosine x, you simply get sine x as your solution. So again, you can double check if you differentiate sine x plus c is a constant, you are going to get cosine x, which is the integrand in this integration. So always look at the solution, take the differentiation of that solution, and you should end up with the original function that you integrated with. As an example, let's try out this one. Cosine, instead of x, we have 2x dx. How are we going to do this one? So again, I'm going to make a substitution. Let's call u equals 2x, and that implies du equals 2 times dx. So that means any place I have dx, I can put 1/2 du. So then I'm going to transform this original integration. Cosine, instead of 2x, I'll put u, and d, instead of dx, I will put 1/2 du. And then I can pull out that 1/2, integrate cosine u du. Now the answer is straightforward, because I'm going to simply apply this rule, 1/2 sine u plus c. But again, u is something that I introduced to the function, so I need to replace that. So the final answer would be 1/2 sine 2x plus c. So that's the answer to this example. Similarly, if we integrate sine x with respect to dx, the answer is minus cosine x plus c. So again, you can try an example like this. Let's say sine 3x dx, and just like the example that I did in the previous for the previous rule, you should get minus 1/3 cosine 3x plus c as the answer. Always remember, if you are not sure, differentiate the solution or the answer and see if you are going to get the original function that you integrated with. So for example, we can double check this. Simply take d over dx of the solution that we have, minus 1/3 cosine 3x plus c, where c is a constant. So then the answer would be minus 1/3. I can pull that out. Then d over dx cosine 3x, and then d over dx for a constant is simply 0. So minus 1/3 d over dx cosine 3x is minus sine 3x times the derivative of the inner function, which is 3. So then you can see 3 in the numerator cancels out with 3 in the denominator. The minus minus becomes plus, and you get plus sine 3x. And that's the original function we started with. This is another rule of integration that will be important in our general physics courses. So remember, this a is a constant, and x is the variable. So let's try out this integration. So let's do a definite integral from 0 to, let's say, 5, and I have 1 over x squared plus 4, the square root of that, and dx. So how are we going to find the answer for this one? So first I'll identify that 4 can be written as 2 squared. So from 0 to 5, integrate 1 over square root of x squared plus 2 squared dx. So then I can directly apply this rule, this result. So ln x plus square root of x squared plus 2 squared. Now, since this is a definite integral, I don't need to add a constant of integration. Simply, I'm going to substitute the lower limit and the upper limit to this result. So then my answer would be ln. First, I'm going to substitute the upper limit and subtract the lower limit values from that. So wherever I have x, I substitute 5 plus square root of 5 squared plus 2 squared minus, now I am going to substitute the lower limit, ln 0 plus square root of 0 squared is simply 0, plus 2 squared. And that would give the answer. So I can further simplify this, ln 5 plus square root of 29, because 5 squared is 25 plus 2 squared is 4, 29, minus ln, simply here I need to take the square root of 2 squared, which is 2. So this would give the final answer. You can use a calculator to solve these numerical values, but that's our final answer. This is the final rule of integration that I'm going to discuss. Again, you need to identify that a is a constant value and x is the variable. We can always show this how we get the this particular solution, but that's not the objective in our general physics course. We simply use this result in our physics problems. So as an example, let's try out this one. Integrate x square root of x squared plus 81 with respect to x. Again, you can identify that 81 can be written as 9 squared. So you have square root of x squared plus 9 squared. You integrate this with respect to x, and this is an indefinite integral. So your answer would look like this: x squared plus 9 squared plus a constant of integration. Now you can always check if your solution is correct simply by taking the derivative of the solution. So d over dx square root of x squared plus 9 squared plus c, where c is the constant of integration. That's going to be 0 when you take the derivative of a constant. So then we only consider the square root term. So that will be 1/2 1 over square root of x squared plus 9 squared, and then the differentiation of this inner function, which is simply 2x. So then the 2 in the numerator and the denominator cancels out. You will get x over square root of x squared plus 9 squared, which is 81. And you can see this is the same function that we have in the integrand. So this solution is correct. So this is a very important thing in integration. When you get your solution, take the derivative of that solution, and that should be the same as the integrand of your integral. Another example that we can try out, another indefinite integral. Let's say we have 2x over square root of 4x squared plus 1. Integrate this with respect to x. So when you get something like this, we have to transform it to a form that we already know. So what I'm going to do is that I'm going to transform this into this form. So I have 2x in the numerator, and I'm going to pull out a 4 from the square root of the denominator. So when I pull out a 4 from the square root, it's going to become a 2. And then inside the square root, I'll have x squared plus, instead of 1, now I'll have 1/4. And then integrate with respect to x. So in this case, you can see the numerator and the denominator, they have 2, so they cancels out. And then I'll have this as my simplified version of the integral. So x squared, and 1/4 I can write as the square of 1/2, like this, and then dx. So now you can apply the rule that we have discussed. So then your answer would be square root of x squared plus 1/2 squared, and always put a c because this is a indefinite integral. So that's your answer for this example. This is the final section in our math primer for general physics. So I'm going to briefly talk about binomial expansion and other types of expansions. So first, let's get an idea about what is a factorial of a number, because you'll come across, for example, this symbol, 2 factorial. We write it like that, and that is defined as 2 times 1, which is 2. If it's 3 factorial, then it's 3 times 2 times 1, which is 6. If it's 4 factorial, then it's 4 times 3 times 2 times 1, which is going to be 24. So you get the idea. If it's like, let's say, an arbitrary n integer number, then it would be n times n minus 1 times n minus 2 times n minus 3, like that. So that's how we define a factorial of a number. Now, binomial expansion is given by this one. So if you have a term like this, you can expand that term. Here the n can be either positive, it can be negative, it can be an integer, or even a non-integer. So as an example, we can think about, let's say, 1 plus x to the power 3. So then you identify that your n is 3, and you substitute for n equals 3. So 1 plus 3x, factorial 1 is simply 1, so I'm not going to write that. This would be 3 times 2 x squared, and then factorial 2 is simply 2, and then you can see the 2's cancels out, and then this can be written as x plus 1 plus x cubed equals 1 plus 3x plus 3x squared plus the other terms. So in physics, sometimes we usually don't need the higher order terms. We are simply fine with having maybe the first order or the second order up to the first order term or up to the second order term. Usually, like when x is very small, you can see when x is very small, then the higher order terms, for example, x squared term, x cubed terms, x to the power 4 term, things like that will be negligible. So that is that comes in physics. Especially like when you look at a certain problem, you can see this x represents a physical quantity. It could be a distance, it could be some sort of a mass, but if it's extremely small, then the square of that term is even smaller. So that's the idea. So usually, like in these expansions, we look up to the first order term. So this is an example where we have to apply binomial expansion. So we are given these two terms and we have to expand them. It's also given that z is much larger than d over 2. So we'll first look at this term, the 1 over z plus term, 1 over z plus d over 2 squared. So how are we going to expand this? The first thing I'm going to do is I'm going to pull out a z from the term in the denominator. So if I pull it out, then it will become z squared, and then I'll have 1 over 1 plus d over 2 times z and the square of the entire thing. Now the second term, I can take the square to the numerator and then its sign, the exponent's sign will change. So I have 1 over z squared. Now I'll have 1 plus d over 2z to the power minus 2. So here you can identify that this is similar to 1 plus x entire thing raised to the power n, where n is equal to minus 2 and x is equal to d over 2z. So with that we can expand this term inside the parenthesis. So if I do that, I'll have 1 over z squared. So that's not going to get involved in the initial part of the expansion. I'll have 1 plus n times x. So n is minus 2. X is d over 2z. And then I will have plus n times n minus 1. N is minus 2. N minus 1 is minus 2 plus minus 1. So that means minus 3. Times x squared. That is our d over 2c squared. And we have to divide this term by factorial 2. So factorial 2 is nothing but 2. So I'm going to divide it like that. In the first term, if you recall, we have to divide by factorial 1. But factorial 1 is simply 1. So that's why I completely ignored that. And then you have the higher order terms, but I'm not going to write down the higher order terms. Now if we consider the given condition z much greater than d over 2, this implies 1 is much greater than d over 2z. So if we have d over 2z squared like in the third term, that is extremely small than 1, almost closer to 0. So as a result, we can consider this third term inside the square brackets as equal to 0. We can neglect that term because of this condition. So then I can write down 1 over z plus d over 2 squared. This is approximately equal to 1 over z squared minus d z cubed. This is valid when z is much greater than d over 2. So this is how we apply binomial expansion to this particular problem. So this is just the first part. So if we look at the second part, so that means we have 1 over z minus d over 2 squared. Again, just like in the first part, I'm going to pull out a z squared term, and then the second part would look like 1 minus d over 2z square of the entire denominator. And then I can again rewrite the second term by taking it to the numerator, and its exponent will become a negative value. So 1 minus d over 2z to the power negative 2. Now again, you should be able to identify that this looks like 1 plus x raised to the power n. If you compare the exponents, you will see that n is equal to negative 2. And if you compare this x term with the d over 2z, you will see that x in this case is negative d over 2c. It's not positive, it's negative. Now we can apply the binomial expansion 1 over z squared. We have 1 plus n times x over factorial 1. N is minus 2. X is minus d over 2z plus n times n minus 1. N is minus 2. N minus 1 is minus 3 times x raised to the power 2, or x squared. So then I have minus 2 over d over 2z squared divided by factorial 2, which is nothing but 2. Again, I'm not going to write down the higher order terms. Now, similar to previous case, we can use that approximation, that condition where c is much greater than d over 2. That implies 1 is much greater than d over 2z. And then from there again, you'll see this third term inside the parentheses is approximately close to 0. And as a result, our term, the expansion of this term, d over 2 squared, is approximately equal to 1 over z squared plus d over z cubed. So this happens when z is much greater than d over 2. So this is how you do the second part of this example. Now let's look at some other expansions. We'll start with the logarithmic expansion. So if you have ln 1 plus x, you can expand it in this way using x terms. Suppose that you have this function ln 1 minus x. How are you going to expand this? What you can do is that you can rewrite this function as 1 plus minus x, ln 1 plus minus x. So then everywhere you find x in the original function expansion, you can substitute minus x for those places. So I can write minus x minus 1 half minus x squared plus 1/3 minus x cubed, and then you have the other terms. So then you'll get ln 1 minus x. After simplifying, you'll get minus x minus 1/2 x squared, because minus x squared is simply x squared, and then you'll have a minus sign 1/3 x cubed. Then the other higher order terms, which I'm not going to write down. Now let's look at the other expansion. So this is the expansion of the exponential function. So for example, if we think about e to the power 5, we can write it as 1 plus 5 plus 5 squared over factorial 2, which is simply 2. Then 5 raised to the power 3 divided by factorial 3, which is 6, like that. Okay, and even like a number less than 1, e to the power 0.5, or let's say minus 0.5, we can again use the expansion to find that 1 plus minus 0.5 plus minus 0.5 squared divided by factorial 2, which is simply 2, plus minus 0.5 raised to the power 3 divided by factorial 3, which is 6. So like this, you can use the exponential expansion. Now let's look at some trigonometric expansions. So here the important thing is theta is given in radians. So it's not in degrees, it's in radians. So for example, if you are looking for sine pi over 3, then how do you find that? You can expand it in terms of pi over 3 minus pi over 3 cubed divided by factorial 3, and then the other term pi over 3 to the power 5 divided by factorial 5. So like that, you can expand trigonometric terms, even like cosine, let's say pi. You have cosine pi. Cosine pi is equal to 180 degrees. So then you can have 1 minus pi squared over factorial 2 plus pi raised to the power 4 over factorial 4. Keep in mind, you cannot do this. Cosine 180 degrees equals 1 minus 180 squared divided by factorial 2 plus 180 raised to the power 4 divided by factorial 4. You cannot do this. This is simply wrong. So that's why this applies when theta is measured in radians. Similarly, we can write the tangent. Let's say tangent pi over 10 equals pi over 10 plus pi over 10 raised to the power 3 divided by 3 plus 2 times pi over 10 raised to the power 5 divided by 15 and the higher order terms. But usually, 3 terms is more than enough, and in physics it depends on the problem. The problem will give you enough information where to truncate this series. Finally, we'll talk about small angle approximation. So this is valid when the angle is less than 10 degrees, or in radians it should be less than 0.17 radians. So for the small angle approximation, we have cosine theta is approximately equal to 1 minus theta squared over 2. Sine theta approximately equal to theta, and tangent theta approximately equal to theta. In all these three cases, remember theta is measured in radians, and theta has to be a small angle. That means it has to be less than 0.17 radians. So if you look at the sine theta and the cosine theta, their right hand sides are equal. So for small angle approximation, we can have sine theta approximately equal to tangent theta. So with that, I conclude the math primer for general physics. So I believe this video gives you a very good idea about the skills that you need to review to succeed in general physics 1 as well as in general physics 2. In my next video, I will talk about SI units, unit conversions, scientific notation, and significant figures. So I'll post that video as soon as possible.